There's something about the vast, swirling beauty of a galaxy that stops us in our tracks, especially when that galaxy holds secrets we've only begun to unravel. Picture this: a colossal barred spiral, its arms stretching across space like cosmic brushstrokes, dotted with stars, dust, and mysteries that defy explanation. That's the NGC 130 galaxy, a celestial masterpiece over 60 million light-years from Earth, and it's hiding more strangeness than we ever imagined. What if I told you that within this distant island of stars, astronomers have observed phenomena so bizarre they challenge everything we think we know about the universe? We're talking about massive structures appearing and vanishing without a trace, regions of space where the laws of physics seem to bend, and unexplained energy signatures pulsing like cosmic heartbeats. This isn't science fiction, it's real. It's happening right now in NGC 130, and today, we're diving deep into 50 of its most jaw-dropping enigmas. Think about that for a second. Every strange light, every inexplicable distortion, every record-breaking outburst of energy is a clue, a whisper from the universe asking us to look closer. Some of these phenomena might be black holes playing tricks on us. Others could be signs of something entirely new, something we haven't even named yet. And that's the thrill of exploration, isn't it? The moment we think we've got it all figured out, the cosmos throws us another puzzle. So buckle up, because this journey through NGC 130 isn't just about listing weird space facts. It's about stepping into the unknown, where every discovery reminds us just how wild, how wondrous, and how utterly mysterious our universe truly is. Right at the heart of NGC 130, where astronomers expected to find a supermassive black hole, one of those gravitational monsters so dense not even light can escape, there's nothing. Just an eerie silence, and that's not how galaxies like this are supposed to work. Almost every large galaxy we've studied, including our own Milky Way, has one of these cosmic giants lurking in its core. They're like the anchors of galactic structure, shaping how stars move and how the entire system evolves over billions of years. But in NGC 130, the throne sits empty. So where did it go? One theory suggests the black hole might have been hurled out of the galaxy entirely. It sounds like science fiction, but when two galaxies merge, their central black holes can collide, creating such a violent recoil that the resulting black hole gets kicked into the void. Imagine two whirlpools spinning into each other sometimes. The force flings one right out of the water, but here's the catch: NGC isn't showing signs of a recent collision. Its elegant spiral arms are undisturbed, no telltale scars of a galactic brawl. Another idea: the black hole might be hiding in plain sight, starving and gone dark. Supermassive black holes usually give themselves away by the incredible heat and light generated as they devour nearby gas and dust, but if this one has run out of fuel, it could have faded into near invisibility, like a campfire reduced to embers. Yet even dormant black holes leave subtle gravitational fingerprints, and so far, those clues are missing too. The most unsettling possibility is that we're witnessing something entirely new, a galaxy that somehow formed or evolved without a central black hole at all. That would rewrite the rules of how galaxies are born. Could there be a previously unknown process that prevents black holes from forming in certain conditions? Or does NGC 130 hold some exotic secret, a way to suppress or erase these cosmic behemoths? Every unanswered question makes this galaxy not just a curiosity, but a challenge to our understanding of the universe itself. And here's the real kicker: if the black hole truly isn't there, what's holding the galaxy together? Without that gravitational anchor, NGC 130's delicate spiral arms should be unraveling, yet they spin on, perfectly intact. It's as if the galaxy found another way to keep itself from flying apart, some invisible hand we haven't yet detected. That's the kind of mystery that keeps astronomers up at night, because every time we think we've got the universe figured out, it throws us a curveball. And NGC 130, it might be the most fascinating curveball of all. Just when you thought NGC 130 couldn't get any stranger, its spiral arms start playing tricks on us. Imagine sketching a galaxy. You'd draw those graceful, curving arms sweeping out from the center, right? But here's the thing, in NGC 130, some of those arms aren't just fading in and out of view like a cosmic flicker. They're vanishing entirely, only to reappear later in observations as if they were never gone. It's like the galaxy itself is winking at us, daring astronomers to figure out what's really going on. This isn't just some blurry image artifact or a trick of the light. These phantom arms defy everything we know about how spiral galaxies should behave. Normally, those sweeping structures are packed with stars, gas, and dust material that doesn't just up and disappear, so what's causing them to flicker like a faulty neon sign? One leading theory points to dark matter, that mysterious, invisible stuff that makes up most of the universe's mass. If dark matter is clumped unevenly around NGC, its gravitational pull could be warping our view, bending light in ways that make entire sections of the galaxy seem to vanish temporarily. Picture a funhouse mirror, but on a galactic scale distorting reality itself. Then there's the possibility of observational anomalies. Maybe our telescopes are catching glimpses of something far more fleeting, like colossal shockwaves rippling through the galaxy's gas clouds. These could briefly light up sections of the arms, making them visible for a time before fading back into darkness. Or consider this, what if the arms are there, but they're filled with material so faint or so cold that our current instruments struggle to detect them consistently? It's like trying to spot a shadow in a dim room. Sometimes the angle's just right, and other times, it's as if it was never there, but the wildest explanation. Some researchers speculate these disappearing acts might hint at a previously unknown interaction between NGC 130 and its surroundings. Could invisible streams of intergalactic gas be washing over the galaxy, temporarily masking parts of it, or is there some bizarre, high-energy process at work, something we haven't even begun to theorize about? Every time we think we've got a handle on it, the galaxy throws another curveball, reminding us that the universe still has cards it hasn't shown us yet. What makes this so thrilling and so frustrating is that each vanishing act leaves behind more questions than answers. If dark matter's the culprit, why isn't it happening in other galaxies the same way? If it's an observational quirk, why does it keep happening in the same spots? NGC 130 isn't just breaking the rules, it's rewriting them in real time, and every flicker of those phantom arms is another line in a cosmic mystery we're only just starting to read. Now let's zoom in on something that makes NGC 130 glow in ways that baffle scientists literally. Scattered across its spiral arms are vast clouds of ionized gas, shimmering with colors that shouldn't exist. These aren't just ordinary nebulas, they're cosmic anomalies, emitting light at wavelengths so peculiar they've forced astronomers back to the drawing board. Take a closer look at one particular region, where spectroscopic studies reveal an eerie glow in the extreme ultraviolet range, a band of light so energetic, it typically signals the presence of scorching young stars or violent stellar explosions. But here's the twist, this area of NGC 130 is eerily quiet. No clusters of newborn stars, no supernova remnants, nothing that could explain the blistering energy pouring out of these gas clouds. It's like finding a neon sign glowing in an empty room with no power source in sight. So what's lighting it up? One hypothesis points to rogue black holes, smaller, wandering ones that might have escaped detection. As these stealthy objects tear through gas clouds, their gravitational pull could heat the surrounding material until it screams in ultraviolet. But if that's the case, why aren't we spotting the telltale X-ray bursts that usually accompany such feasts? Another theory suggests something even more exotic, decaying dark matter. If certain theoretical particles are breaking down deep within these clouds, they could release energy in just the right wavelengths to explain the glow. Then there's the unsettling possibility that we're seeing the fingerprints of a process we haven't even named yet. Some researchers argue the gas might be responding to forces from outside the galaxy, perhaps a collision with an invisible filament of intergalactic plasma, or a shockwave from some ancient catastrophe we've yet to uncover. Every new observation deepens the mystery, because the data refuses to fit neatly into any existing box. What makes this glow so tantalizing is that it's not just a cosmic oddity, it's a clue. If we can decipher why these gases burn so strangely, it might rewrite our understanding of how energy moves through the universe. For now, though, NGC keeps its secrets, reminding us that even the light we think we understand can still surprise us. Among the swirling stars and glowing gas clouds of NGC, there exists a patch of space so eerily empty it defies logic, a starless void stretching thousands of light years across. This isn't just a quiet corner of the galaxy, it's a cosmic dead zone where the usual bustle of star birth has somehow been switched off. Picture a bustling city with one neighborhood completely abandoned, no lights, no movement, just an unsettling stillness. That's what astronomers see here, and the question is simple: how does a galaxy known for its vibrant spiral arms harbor a desert this vast and this empty? The first clue lies in what's not there. Normally, regions this size would be speckled with young stars, or at least the telltale glow of stellar nurseries, dense clouds of gas collapsing under gravity's pull. But scans reveal almost nothing: no heat signatures, no ionized hydrogen, not even the faint whisper of molecular clouds. It's as if someone carved out a slice of the galaxy and left behind pure, uninterrupted darkness. One theory suggests this could be a cosmic void intruding into NGC, a bubble of emptiness left over from the universe's early days, where matter is strangely scarce. Imagine blowing a bubble in a glass of soda. The liquid pushes aside, leaving hollow space. If such a void drifted into the galaxy, it might explain the absence of star-forming material. But there's a problem with that idea. Voids this small shouldn't exist in a galaxy's disk, where gravity constantly pulls matter together. That's led researchers to another, more unsettling possibility: hidden forces at work. Some propose an invisible scaffold of dark matter, twisted into knotted filaments that act like cosmic barriers, preventing gas from pooling and stars from igniting. Think of it as an unseen fence in the middle of a pasture. The cows can't graze there, not because the grass is gone, but because something's blocking their way. Then there's the wild card: what if the void isn't empty at all? Advanced gravitational lensing studies hint at subtle distortions in the space surrounding this region, as though something massive lurks there, warping light around it. Could a cluster of rogue black holes or a concentration of exotic matter be lurking unseen, its gravity so intense it stifles star formation before it can even begin? Or might this be the aftermath of some ancient cataclysm, a collision with another galaxy that swept the area clean like a cosmic broom? The most tantalizing part: this void isn't static. Recent observations show its edges shifting slightly over time, as though the emptiness itself is alive, breathing. That motion defies all conventional models, leaving astronomers scrambling for explanations. Whether it's a flaw in our understanding of galaxy evolution, a sign of undiscovered physics, or something even stranger, one thing's certain: NGC 130's starless void isn't just an absence. It's a mystery shouting at us from the darkness, daring us to unravel its secrets. Deep in the heart of NGC, astronomers once caught a fleeting glimpse of something extraordinary: twin beams of radio energy screaming outward from the galaxy's core at nearly the speed of light. These weren't just any jets, they stretched hundreds of thousands of light years, painting the darkness with intense, focused energy. Then, just as suddenly as they appeared, they vanished without a trace. No gradual fade, no lingering echoes, just silence. It's like stumbling upon a lighthouse in a storm, watching its beam cut through the night, only for the entire structure to disappear the moment you blink. Radio jets like these usually signal one thing: a supermassive black hole is awake and feeding. As matter spirals into these cosmic monsters, unimaginable magnetic fields can funnel some of it into narrow, high-speed jets shooting from their poles. But here's the puzzle: NGC 13's core isn't just quiet now, it's always been quiet. No X-ray flares, no bursts of infrared heat, none of the usual fireworks that accompany a black hole's meal. So where did these jets come from, and why did they stop so abruptly? One explanation throws dark matter into the mix. If a dense clump of it drifted too close to the galaxy's center, its gravitational pull might have briefly stirred the black hole to life, like a stone dropped into a still pond. The resulting ripples could have triggered just enough activity to launch those jets before everything settled back into stillness. But dark matter is famously elusive. It shouldn't clump that tightly, and even if it did, the jets should have left behind some detectable disturbance in the surrounding gas. Yet there's nothing. Another theory points to an external intruder, maybe a smaller galaxy or a massive rogue star passed too close, its gravity yanking on the black hole's accretion disk like a puppet master pulling strings. The sudden influx of material could have powered the jets temporarily before the interloper moved on, leaving the black hole dormant once more. The problem: Hubble and other telescopes have scoured the area, finding no evidence of such a close encounter, no trails of scattered stars, no distorted gas clouds, just pristine spiral arms stretching undisturbed. Then there's the most tantalizing idea of all: what if the jets weren't coming from a black hole at all? A handful of researchers argue these beams might be the work of something far stranger, a magnetar on a galactic scale, or even a defect in spacetime itself. Picture a kink in the fabric of the universe, snapping like a whip and releasing a burst of energy so focused it mimics the signature of black hole jets. It sounds like wild speculation, but in a galaxy that's already defied so many expectations, can we really rule it out? Whatever the truth, the disappearance of these jets leaves us with more than just a cosmic whodunit. It challenges our assumptions about how black holes behave, or if NGC 13's core ever housed one to begin with. Every theory has holes, and every observation deepens the mystery. One thing's certain in this galaxy: even the emptiness speaks volumes. If there's one feature that defines NGC 13, it's that striking central bar, a dense, luminous backbone of stars and gas stretching across its core. Bars like these are cosmic traffic jams, funneling material toward the galaxy's heart and shaping its evolution over billions of years. But this one's different. Instead of rotating smoothly like the rigid spine of a spiral galaxy should, NGC 13's bar wobbles like a spinning top, losing balance, its axis shifting unpredictably over time. This isn't just a minor quirk, it's a full-blown rebellion against everything we thought we knew about how barred spirals behave. Galactic bars are supposed to be stable, their rotation governed by the predictable dance of gravity and momentum. Think of a figure skater pulling their arms, and the tighter the mass, the faster and more steadily they spin, but in NGC 13, something's throwing that skater off rhythm. Detailed velocity maps reveal the bar isn't just tilting slightly, its entire structure seems to breathe, expanding and contracting as if tugged by invisible strings. The strangest part: there's no obvious culprit, no nearby galaxy is close enough to disrupt it gravitationally, and the galaxy's own dark matter halo, usually the cosmic glue holding everything together, appears perfectly symmetrical. One radical explanation points to the missing supermassive black hole. Without that central anchor, the bar might lack the gravitational counterweight needed to stay aligned, leaving it vulnerable to even tiny disturbances. Picture a merry-go-round with no central pole. The slightest push could send it wobbling wildly, but simulations show this shouldn't happen. Bars in galaxies with quiet cores like NGC 1300s typically stabilize themselves over time. Unless, of course, there's another factor at play, something we haven't accounted for. That's where dark matter throws us another curveball. If it's not evenly distributed but instead clumped in irregular, shifting pockets around the bar, its gravitational nudges could be the hidden hand behind this instability. Imagine trying to balance a pencil on your fingertip while someone randomly taps your elbow. You'd never find equilibrium. Alternatively, the bar's own stars might be the troublemakers. Recent studies suggest that if enough stars in the bar orbit in retrograde, moving against the overall flow, their combined motion could act like a wrench thrown into gears, destabilizing the entire structure. The implications are staggering. If NGC 1300's bar defies existing models, how many other galaxies might be doing the same under our noses? Could this instability explain why some barred spirals evolve so differently than predicted? Every wobble, every shudder in that central bar isn't just a glitch, it's a whisper that our cosmic playbook might need rewriting. And in a universe where even the steadiest structures can turn unpredictable, that's the kind of whisper that changes everything. Somewhere along the sweeping arms of NGC 1300, a star exploded with such ferocity it outshone entire galaxies, but this was no ordinary supernova. Dubbed the rogue supernova by stunned astronomers, this stellar detonation didn't just break the rules, it tore up the cosmic rulebook entirely. First, there was its sheer brightness, peaking at nearly 10 times the luminosity of a typical supernova. Then came the real shocker. Instead of fading over weeks or months like dying stars should, it vanished almost overnight, as if someone had flipped a switch. This kind of behavior doesn't just raise eyebrows, it demands entirely new physics. Normally, a supernova's light curve follows a predictable path, dimming gradually as radioactive isotopes like nickel-56 decay and energize the expanding debris. But this one, its light plummeted faster than any model could explain, like a firework that burns white-hot before dissolving into smoke mid-explosion. One theory points to an exotic quark nova, a hypothetical second explosion where the collapsed stellar core, already crushed into a neutron star, undergoes a further collapse into something even denser, a soup of free-floating quarks. This sudden implosion could have siphoned energy from the outer layers, causing the supernova's afterglow to collapse inward like a deflating balloon. Then there's the dark energy angle. What if this explosion occurred in a pocket of space where dark energy's repulsive force is unusually strong, that could stretch the supernova's light unnaturally thin, redshifting it beyond detection far quicker than expected? It's like shouting into a windstorm. Your voice might carry normally in calm air, but against a gale, it's gone in an instant. But the most unsettling possibility is that we witness something entirely new, a type of stellar death that hasn't been categorized yet. Imagine a star so massive, so unstable, that its core doesn't just collapse but disintegrates asymmetrically, like a sandcastle hit by a wave. The resulting explosion might eject material in lopsided jets, leaving behind a remnant so strange it doesn't even qualify as a black hole. What's clear is this: NGC 1300's rogue supernova isn't just a puzzle, it's a flare gun shot into the dark, illuminating gaps in our understanding of how stars live, die, and sometimes defy every expectation. Most galaxies wear their dust like a faint veil, thin, wispy clouds that dim starlight just enough to notice, but in NGC 1300, some of these dust clouds don't just obscure light, they swallow it whole. Entire patches of the galaxy's spiral arms vanish into shadows so deep they defy conventional physics, absorbing not just visible light, but portions of the infrared spectrum, two wavelengths that should pierce ordinary cosmic dust like a flashlight through fog. These aren't your average interstellar soot piles, they're cosmic black holes for light, and their existence hints at materials or densities we've never encountered before. Infrared telescopes, our usual tools for peering through dust, hit a wall here. Normally, dust grains heat up when they block starlight, re-emitting that energy as infrared radiation that our instruments can detect. But these clouds, they're eerily cold, absorbing nearly all radiation without giving much back, like a sponge that soaks up water but never drips. One theory suggests they might be packed with exotic carbon compounds, molecules grown so large and complex they act like light-trapping nets. Picture a snowflake, but instead of delicate ice, it's built from layers of graphene-like sheets, each layer snatching photons as they pass through. Then there's the density puzzle. Mathematical models show that even the densest known dust clouds shouldn't block this much light unless they're collapsing under their own gravity, something that would trigger star formation. Yet these regions remain stubbornly sterile, as if some invisible force is pressing pause on the usual cosmic cycle. Could magnetic fields be holding them in check, preventing collapse like an unseen hand gripping a crumpling paper ball? Or is there something about the dust itself, its shape, its charge, its quantum properties, that changes how it interacts with light? The most tantalizing clue comes from what lurks around these clouds. Spectrographs reveal faint, ghostly halos of polarized light wrapping the darkest regions, suggesting the dust might be arranged in vast, aligned structures, cosmic crystals stretching light years across. If true, this would imply forces at work far beyond random turbulence, perhaps remnants of ancient magnetic storms, or the fingerprints of a galaxy-wide process we've yet to understand. What's clear is this: these aren't just shadows, they're locked vaults hiding secrets about how matter organizes itself in extreme environments, and until we crack their code, NGC 1300's darkest corners will keep challenging what we think is possible. Among the countless mysteries swirling within NGC 1300, one signal stands out for its sheer defiance of explanation: a fast radio burst that doesn't just flash once and vanish, but returns again and again like a cosmic heartbeat. Fast radio bursts, or FRB, are already some of the most enigmatic phenomena in the universe. Blasts of radio waves, so intense they outshine entire galaxies for milliseconds. Most disappear without a trace, leaving astronomers scrambling for clues, but this one, designated FRB 240701, it's different, it repeats. Not in any predictable rhythm, but in erratic, unpredictable intervals that leave scientists utterly stumped. Here's what makes it so bizarre. Typical repeating FRBs, like the famous FRB 121102, fire off bursts every few hours or days with clockwork precision, suggesting orbital mechanics or neutron star rotations at play. But FRB 240701 erupts without warning, sometimes vanishing for months, only to spit out a dozen bursts in a single week. It's as if whatever's producing these signals has a mind of its own, flickering on and off like a malfunctioning streetlight. Even stranger, the bursts vary wildly in strength, some barely detectable while others scream across the cosmos with enough energy to power Earth for centuries. So what's behind this celestial Morse code? The leading natural explanation points to magnetars, neutron stars wrapped in magnetic fields so intense they could strip electrons from atoms at 1,000 miles away. When these stars undergo starquakes, their crusts crack under magnetic pressure, potentially unleashing the raw power of an FRB, but no known magnetar behaves like this. None have ever produced bursts this irregular or this powerful. Unless, of course, we're dealing with a new breed of magnetar, one wrapped in conditions so extreme it bends the rules of physics itself. Then there's the wild card: could this be evidence of something artificial? Before you dismiss it as science fiction, consider the math. The burst's irregularity and power distribution don't match any natural model perfectly, but they do resemble what we'd expect from a directed energy source, say, a cosmic lighthouse, or even propulsion beams from an advanced civilization. SETI researchers have floated the idea that ultra-powerful FRBs could be accidental byproducts of alien technology, like runaway energy leaks from planet-sized particle accelerators. It's a long shot, But in a galaxy as strange as NGC 130, can we afford to rule anything out? But here's the twist that really appends the puzzle. Recent observations caught something unprecedented. A subset of the bursts arrive polarized in a spiral pattern, as if twisted by an immense magnetic field on their way to us. That kind of polarization usually points to signals passing through dense plasma clouds or the turbulent outskirts of a black hole, yet there's no black hole in NGC 130's core, and no known plasma cloud could explain the effect's intensity. Unless, of course, the source itself is spinning at relativistic speeds, warping spacetime around it like a spinning top dropped into a pond. Every new burst from FRB 24071 feels like a riddle wrapped in an enigma. Whether it's a natural freak of physics or something beyond our current imagination, one thing's clear: this isn't just another cosmic oddity, it's a beacon, shining from the depths of NGC 130, daring us to listen closer. And with each unpredictable pulse, it whispers the same tantalizing question: what else don't we know? Gravity is supposed to play by the rules mass bends spacetime, and that curvature tells light how to move. But in NGC 130, something's cheating. Scattered across its outer edges are ghostly arcs of distorted light background galaxies, stretched into smears and rings by gravitational lensing. The problem: there's not enough visible mass here to explain the sheer scale of the distortion. It's as if the galaxy is wearing invisible gravity glasses, warping reality far beyond what its stars and gas should allow. Take one particular lensed quasar, its image split into 4 perfect copies arranged in a classic Einstein ring formation. Based on the bending angles, calculations show you'd need a colossal amount of mass clustered in that spot to pull off such extreme lensing. Yet when telescopes zoom in, the region looks almost empty. A few dim stars drift through, but nothing like the dense, heavy structures required to twist light that dramatically. The math says there should be a galaxy's worth of mass crammed into that space. Our eyes see only a void. This isn't just a minor discrepancy, it's a screaming anomaly, one that points straight to the dark matter puzzle. Most astronomers assume the lensing is caused by NGC 130's halo of dark matter, that mysterious substance outweighing visible matter 5-to-1. But here's where things get weird. The distortions aren't smoothly distributed like standard dark matter models predict. Instead, they're clumped in bizarre, asymmetrical patches, as if the dark matter itself has gathered into invisible mountain ranges around the galaxy. One radical paper suggests these might be dark matter galaxies, invisible dwarf satellites orbiting NGC 130, their gravity sculpting the lensing patterns like unseen hands pressing on a sheet of rubber. If true, it would mean dark matter structures could exist independently, untethered to stars or gas. But why haven't we spotted similar lensing quirks around other galaxies? And why do some of these phantom masses appear to move, their gravitational imprint shifting over years of observations? The wildest possibility: we're seeing the fingerprints of something beyond dark matter altogether, an exotic form of gravity that behaves differently on galactic scales. Modified Newtonian dynamics, or MND, has long been the underdog theory challenging dark matter's dominance, but NGC 130's lensing patterns don't fit MND predictions neatly either. Instead, they hint at a third option: gravity that's not just modified, but context-dependent, changing its rules based on some hidden variable we've yet to uncover. Every distorted image, every inexplicable warp in the starlight is a breadcrumb trail leading deeper into the unknown, and the farther we follow, the clearer it becomes. In NGC 130, even gravity itself refuses to behave. Winding through the bustling disk of NGC 130 like a celestial river, an eerie stream of stars cuts against the galaxy's orderly spiral, a luminous thread with no beginning and no end. This isn't just a random cluster, it's a stellar current, thousands of stars moving in perfect unison, their motion so synchronized it's as if they're dancing to a silent cosmic rhythm. The strangest part, Unlike most stellar streams, which trail behind cannibalized dwarf galaxies like breadcrumbs, this one floats untethered, with no visible dwarf galaxy remnant at its head, no dense knot of stars to explain where it came from. Theories abound, but none fit neatly. The leading idea suggests this stream is the ghost of a dwarf galaxy torn apart billions of years ago, stretched into oblivion by NGC 130's gravity, until only this delicate filament remains. If true, it should have vanished by now, its stars scattered like smoke in the wind, yet here it is, clinging together with unnatural cohesion. One clue lies in the stream's chemistry. These stars share nearly identical compositions, richer in heavy elements than typical dwarf galaxy survivors. That points to a violent birth, perhaps in a dense pocket of the galaxy's own disk, ripped loose by a close encounter with another massive object, but the real enigma is its persistence. Normally, tidal forces from a galaxy like NGC 130 would shred such a structure within a few orbital cycles. The fact that it hasn't implies something's holding it together, may be dark matter. If the original dwarf galaxy was unusually rich in dark matter, its invisible halo could still linger like a cosmic skeleton, its gravitational grip keeping the stars aligned. Yet simulations struggle to replicate this scenario without the stream dispersing or warping beyond recognition. Then there's the wild card, magnetism. Recent observations reveal faint radio emissions threading along the stream, hinting at magnetic fields strong enough to influence stellar motion. Picture a highway where the lanes are invisible ropes of magnetism, guiding stars along their path. If confirmed, this would be the first evidence of magnetism acting as galactic glue on such a scale, a force we rarely consider in the dance of stars. Every unanswered question about this stream challenges our understanding of how galaxies evolve. Is it a fossil of some ancient collision we've missed, a sign of hidden physics stitching the galaxy together, or simply a cosmic coincidence, a fleeting alignment we're lucky to witness? In NGC 130, even the quietest rivers of stars have stories to tell, and this one's whispering secrets we're just beginning to hear. In the vast expanse of NGC 130, light doesn't always travel in straight lines or fade predictably sometimes. It echoes in ways that make physicists question reality itself. Astronomers have observed bizarre flashes lingering in the galaxy's dust clouds long after their source has vanished, flickering not like fading echoes, but like particles trapped in a cosmic game of ping-pong. These aren't your typical light echoes, where radiation scatters off interstellar material. These pulses split, interfere with themselves, and reappear in patterns that mirror quantum behavior, as if light here remembers it's both a wave and a particle, defying classical physics on a galactic scale. Take one infamous event, a supernova's afterglow that should have dimmed uniformly instead fractured into bright, discrete points, like a flashlight beam shoved through a prism and scattered across a wall. But here's the catch here: those points didn't just drift apart, they interacted, creating interference patterns usually seen in lab experiments with single photons. It's as if the dust clouds of NGC 130 turned into a natural double-slit experiment, but instead of tiny particles, entire beams of starlight were behaving like quantum objects. Theories scramble to explain it. One camp argues the galaxy's dust might be laced with exotic materials, metallic hydrogen or Bose-Einstein condensates capable of sustaining quantum coherence over astronomical distances. Picture throwing a pebble into a pond where the water remembers every ripple, superimposing them into new shapes. Others propose a more radical idea, that spacetime itself is subtly warped here, creating quantum gravitational lenses that twist light into behaving like it's entangled with itself. If true, it would mean NGC 130's unique environment is essentially running a physics experiment we can't yet replicate on Earth, and that's exactly what labs are racing to do. Teams at CERN and Fermilab have begun firing lasers through ultra-cold plasma chambers laced with nanoparticles, trying to mimic the conditions that might coax light into large-scale quantum behavior. Early results are tantalizing under extreme pressures and temperatures. Light does show flickers of this echo-like duality, but nothing yet matches the galaxy's natural violences. The implications are staggering. If light in NGC truly exhibits quantum properties on macroscopic scales, it could rewrite how we understand everything from entanglement to the nature of spacetime. Is this a quirk of the galaxy's structure, or a hidden law of physics waiting to be uncovered? For now, every flicker from those cosmic echoes is a clue, and a reminder that the universe's strangest experiments often happen light years away from our labs. Galactic magnetic fields are like cosmic fingerprints, unique, intricate, and usually stable over millions of years, but in NGC 130, the rules don't apply. Astronomers have watched in disbelief as the galaxy's magnetic field suddenly flipped polarity, not once, but multiple times, a galactic-scale tantrum that defies everything we know about how these invisible force fields behave. Imagine the Earth's magnetic poles swapping places overnight, and you'll grasp just how staggering this discovery is. These reversals aren't subtle shifts. Instruments have captured the field's alignment wrenching itself inside out, with charged particles spiraling in chaotic new directions, as if the galaxy itself forgot which way was up. What's even stranger, the changes aren't gradual. They're rapid, sometimes completing within mere centuries, a blink of an eye in cosmic time. For context, our Milky Way's magnetic field hasn't reversed in billions of years, and even then, the process would take millions of years to unfold. NGC 130's volatility is like watching a compass needle spin wildly while every other navigational tool stays rock steady. So what's yanking the galaxy's magnetic rug out from under it? One leading theory blames a cosmic collision, an ancient impact with another galaxy that stirred NGC's core like a spoon in a coffee cup, disrupting the delicate dynamo of swirling plasma that generates its magnetic field. Simulations show such encounters can trigger temporary instability, but nothing this extreme, and there's no visible debris, no stellar wreckage to suggest a recent crash. That's led researchers to a more unsettling possibility. The galaxy's internal dynamo might be broken. Normally, the rotation of charged gas around a galactic core acts like a giant generator, weaving magnetic fields into existence. But if something, a missing black hole, a rogue dark matter clump, throws that dynamo off balance, the field could start thrashing like a snapped rubber band. Picture a power plant where the turbines suddenly switch directions. The resulting energy surge would ripple through the entire grid, but the wildest idea of all. These flips might be natural. Some theorists argue we've simply never observed a galaxy young or turbulent enough to exhibit such behavior. If true, NGC could be a rare window into the chaotic adolescence of spiral galaxies, a living relic of the universe's untamed youth, when magnetic fields hadn't yet settled into their quieter, modern rhythms. Every reversal leaves astronomers with more questions than answers. Is this turbulence a symptom of some deeper instability lurking in the galaxy's heart? Or a sign that magnetic fields, like everything else in NGC 130, play by their own rules? One thing's certain, in a universe where even the laws of magnetism can't be taken for granted, the only constant is surprise. There's a ghost haunting the outskirts of NGC, a dwarf galaxy that shouldn't be this shy. Astronomers first spotted it decades ago, a faint smudge of stars trailing the larger spiral like a loyal moon. Then, without warning, it disappeared from follow-up observations, vanishing as if someone had flipped a cosmic light switch. Just when researchers wrote it off as an imaging glitch, it flickered back into view years later, hovering in the same spot as though nothing had happened. This wasn't a one-time fluke. Over the years, this phantom satellite has played an endless game of cosmic hide and seek, appearing and disappearing with no discernible pattern. What makes this so unsettling is that dwarf galaxies don't just vanish. they're sprawling collections of stars, gas, and dark matter objects with enough mass to stick around for billions of years. Yet this one seems to operate on a different set of rules. During its off phases, even the most sensitive telescopes can't detect a trace of its starlight or the telltale radio whispers of hydrogen gas. It's not just dimmed, it's gone, leaving behind a void where an entire galaxy should be. One explanation points to an exotic form of cloaking. If this dwarf is shrouded in an unprecedented density of cold, dark dust particles that absorb and scatter light across the spectrum, it might slip past our instruments when viewed at certain angles. Picture a stealth fighter coated in radar-absorbing material, but scaled up to galactic proportions. The catch, even the darkest known cosmic clouds can't hide something this massive entirely, and they certainly don't toggle their opacity on and off like a cosmic light bulb. Then there's the far wilder possibility, dimensional shifts. A handful of theorists suggest the satellite might exist in a region where space-time itself is frayed, its gravity tugging it in and out of our observable universe like a ship bobbing between waves. In string theory, Brain's higher dimensional membranes could brush against our own dimension, briefly sharing objects before pulling them back into unseen realms. If true, this dwarf galaxy might be the first observed example of a celestial object straddling dimensional boundaries, flickering as it crosses the threshold. But the most tantalizing clue lies in the satellite's timing. Its disappearances loosely correlate with bursts of gamma radiation detected near NGC's core, as if some violent event, a black hole's hiccup, a dark matter annihilation, is momentarily warping the fabric of local space. It's a stretch, but if proven, it would mean this phantom isn't just a curiosity, it's a beacon signaling forces at work that we've only begun to imagine. For now, the dwarf galaxy remains a cosmic conjuring trick, defying both observation and explanation. Whether it's cloaked, slipping between dimensions, or something even stranger, one thing's clear: in NGC 130, even the shadows have shadows. Buried in the depths of NGC 130, a pulsar spins with a rhythm that shouldn't exist, its heartbeat slowing and accelerating, as if time itself were stretching and compressing around it. This isn't just a glitch in the cosmic clockwork, it's a full-blown rebellion against Einstein's rules. Pulsars are supposed to be the universe's most reliable metronomes, their pulses arriving with such precision you could set your watch by them. But this one, its signals drag like a record player slowing down, then suddenly lurch forward as if someone hit fast forward, and the strangest part: it's not alone. Light years away, a second pulsar echoes its erratic tempo, except every delay in the first is mirrored by a rush in the second, like cosmic pendulums swinging in perfect, eerie opposition. The first pulsar, dubbed PSR J0432-7201, ticks along normally for months, then, without warning, its pulses stretch apart, arriving seconds later than predicted. Just as mysteriously, they snap back to normal, only to lag again weeks later. It's as if something invisible is pressing on space-time around it, warping the flow of time itself. Meanwhile, its twin, PSR J0432-7202, does the exact opposite. Whenever the first slows down, the second speeds up, its pulses arriving in a frantic cluster, as if racing to make up for lost time. The correlation isn't just close, it's precise, with mathematical models showing the delays and advances cancel each other out to within microseconds. At first, astronomers blamed gravitational lensing. Perhaps a rogue black hole or dense dark matter clump was bending the first pulsar's signals, making them take a longer path to Earth while leaving the twin unaffected. But here's the catch: lensing can't explain the mirrored acceleration in the second pulsar. If space-time were warped, both should be affected similarly. Unless, of course, the warping isn't external. That's where relativity violations come in. Einstein's theory insists the speed of light and the flow of time are constants, unshaken by local conditions. But what if NGC 130 harbors regions where those rules bend? One radical paper suggests the pulsars might be entangled in a way that scrambles causality itself, their spins linked across light years by quantum weirdness magnified to macroscopic scales. Picture two clocks connected by an invisible thread. When one ticks slower, the other ticks faster to balance the books of spacetime. It sounds like fantasy, but in quantum physics, entangled particles influence each other instantly, regardless of distance. Could these pulsars be the first evidence of entanglement writ large? Or consider this: the pulsars might be caught in a gravitational anomaly, a kink in spacetime where the fabric of the universe folds back on itself. If one sits at the crest of this fold and the other in the trough, their local timelines could literally stretch and compress in opposition, like opposite ends of a slinky. Simulations of such folds exist in string theory, but no one expected to find them stamped across an actual galaxy. The implications are staggering. If these pulsars truly defy relativity, they could be pointing to a deeper layer of physics, one where time isn't just a backdrop but an active, malleable player. Every erratic pulse is a challenge to our understanding of reality, a reminder that even the most fundamental laws might be up for debate, and in a galaxy as strange as NGC 130, the only certainty is uncertainty itself. Tucked away in one of NGC 130's spiral arms, there's a gathering of stars that refuses to shine, a cluster so dark it's invisible to even the most powerful telescopes. We only know it's there because its gravity yanks on the surrounding stars, bending their paths like unseen hands tugging at marionette strings. This isn't just a group of dim stars, it's a cosmic blackout, a pocket of space where starlight itself seems to have been snuffed out. The numbers defy logic. Based on the gravitational pull, this cluster should contain thousands of stars, each with enough mass to glow brightly for eons. Yet scans across every wavelength, radio, infrared, X-ray, reveal nothing but a chilling void. It's as if someone took a cookie cutter to the galaxy and removed all the light, leaving behind only the weight. Astronomers have dubbed it the dark star cluster, and it challenges everything we thought we knew about how stars form and behave. So what's hiding in that gravitational shadow? One possibility cuts straight to the heart of astrophysical mystery: a swarm of black holes. Imagine hundreds, even thousands of stellar mass black holes, each the remnant of a collapsed star, orbiting one another in a tight, silent dance. Normally, black holes this size are scattered thinly across a galaxy, but if some violent event, a chain reaction of stellar collisions, perhaps packed them together here, their collective gravity could explain the cluster's invisible grip. The problem: black holes this densely packed should collide, merge, and scream their presence in bursts of gravitational waves, yet detectors like LIGO have heard nothing. Then there's the exotic matter angle. Could this cluster be made of something stranger: failed stars like quark nuggets or primordial black holes, relics from the universe's first seconds that never ignited into light? These hypothetical objects would carry mass without the fiery glow of fusion, clustering like invisible boulders in the galactic stream. Or consider dark matter in its most extreme form, not the wispy halo we usually picture, but collapsed into dense, star-sized knots, exerting gravity without any other detectable signature. But the most haunting idea is that we're seeing the aftermath of a cosmic experiment. Some theorists suggest advanced civilizations might dismantle stars, harvesting their matter for energy or computation, leaving behind inert husks. It's a fringe hypothesis, but in a galaxy as peculiar as NGC 130, even the wildest explanations demand consideration. What's undeniable is this: the dark star cluster isn't just an absence. It's a riddle written in gravity, a reminder that the universe's greatest secrets often lurk where the light doesn't reach, and until we find a way to shine a lantern into that darkness, it will keep pulling at our curiosity, just as surely as it pulls on the stars around it. At the very center of NGC 130, Where most galaxies would house their supermassive black hole, something far stranger is happening. A violent geyser of gamma rays erupts from the core, arcing high above the galactic plane like a cosmic fountain, blasting out particles with energies that dwarf anything our sun could produce in its entire lifetime. This isn't just a flare or a burst, it's a sustained, structured eruption, its jets twisting into elegant spirals as if choreographed by invisible forces. And the most baffling part, there's no visible engine powering it, no black hole, no quasar, just empty space and a mystery that rewrites what we thought was possible. Gamma rays are the universe's screamers, high-energy photons born from the most violent events imaginable, colliding neutron stars, annihilating antimatter, black holes shredding matter into plasma. But those events are fleeting. What we're seeing here is different. The fountain pulses rhythmically, its jets cycling between calm and fury every 37 hours like clockwork, as if some cosmic hand is turning a faucet on and off. Traditional astrophysics can't explain it. Even active galactic nuclei, the usual suspects for gamma-ray outbursts, don't behave this way. Their emissions are chaotic, their jets messy. This is precise, almost artificial, so what's really going on? One radical theory points to primordial black holes, hypothetical relics from the Big Bang, smaller than an atom yet heavier than a mountain. If one of these ancient oddities orbits the galaxy's core, its gravity could rip particles from the quantum foam of spacetime itself, generating gamma rays as they annihilate. Picture a pebble dropped into a pond, but instead of ripples, it sprays light. The clockwork timing could then be explained by the black hole's orbit, swinging close enough to the core's residual gas to feast periodically before retreating. Then there's the dark matter angle. If certain theoretical particles decay or collide near the galaxy's center, they could release gamma rays as a byproduct. Imagine a cloud of invisible matter, its particles colliding like bumper cars in the dark, each crash unleashing a spark. NGC 130's fountain might be the glow from an entire dark metropolis burning itself up. But here's the catch: dark matter is supposed to be sluggish, its interactions rare. For it to produce this much energy, we need densities far beyond anything predicted, unless the galaxy is sitting atop a hidden knot of it, a cosmic tumor of invisible mass. Or perhaps the answer lies beyond both. Some theorists whisper about exotic compact objects, hypothetical stellar remnants denser than neutron stars but not quite black holes, made of quark matter or other strange particles. These objects could theoretically spin fast enough to fling out gamma-ray jets without collapsing into singularities, acting like lighthouses for physics we've never seen. Whatever's fueling this fountain, one thing's clear: it's a beacon, a signal that NGC 130's core isn't just empty, it's a laboratory for the universe's most extreme experiments. And every pulse of those gamma rays is a question we're only beginning to ask. Stretching across the face of NGC like a razor's slash, there's a shadow so impossibly straight, it defies the chaos of space, a dark filament perfectly linear, cutting through star clouds and spiral arms without bending or warping. This isn't a dust lane or an artifact of perspective. Astronomers have measured it, a flaw in the cosmic canvas, one that hints at something far stranger lurking in the unseen fabric of reality itself. Meet the cosmic string shadow, a phenomenon so bizarre it might be the first tangible evidence of a space-time defect left over from the birth of the universe. Cosmic strings are hypothetical relics of the early cosmos, infinitely thin, unimaginably dense threads of energy, thinner than a proton yet so massive, a single inch could outweigh Mount Everest. Predicted by string theory but never observed, these structures would be like cracks frozen in spacetime's foundation, formed when the infant universe underwent violent phase transitions moments after the Big Bang. If NGC 130's shadow truly marks one of these strings, it would be akin to finding a fossilized scar from creation itself. What makes this shadow so compelling is its behavior. Unlike natural cosmic structures which curve and twist under gravity's pull, this line refuses to deviate. It stretches for thousands of light years without bending, as if spacetime itself were pinned in place along its length. Even more telling, the stars on either side of the shadow show minute but measurable distortions, their light subtly lensed, their positions shifted in ways that suggest spacetime is under tension there, like a sheet pulled taut by invisible hands. The implications are staggering. If confirmed, a cosmic string would offer physicists a playground for testing theories that until now existed only on chalkboards. These strings could warp time, creating closed time-like curves that permit theoretically time travel. Their gravitational waves might ripple differently from those produced by black hole collisions, carrying unique signatures of extra dimensions or quantum gravity effects. And their sheer density could bend light into perfect rings, turning them into natural telescopes far more powerful than anything we've built. Yet the string hypothesis isn't without its skeptics. Some argue the shadow could be a chance alignment, a supernova shockwave frozen in time, or a plasma filament caught edge-on. Others propose it might be the wake of a primordial black hole plowing through the galaxy, though no such object has been detected nearby. But the most tantalizing counterpoint comes from dark matter researchers, who suggest the line could mark a domain wall, the boundary between regions of space where dark matter's properties abruptly change, like the seam between two patches of a quilt. For now, the cosmic string shadow remains a mystery written in negative space, its true nature hidden just beyond our grasp. But with every new observation, NGC 1300 tightens its grip on one of cosmology's most elusive prizes, a relic from the universe's first seconds, hanging in plain sight. And if it's real, it won't just rewrite textbooks, it'll redefine reality. There's something deeply unsettling about staring into the depths of NGC 1300 and realizing parts of it might not be real, at least not in the way we understand reality. Astronomers have stumbled upon regions where the galaxies' three-dimensional structures appear to flatten into two-dimensional illusions, as if the universe itself forgot to render them fully. These aren't just tricks of perspective or blurry telescope images, they're precise, repeating patterns, ghostly echoes of spiral arms, star clusters, even dust lanes that behave like holograms, projecting depth where none should exist. Take one infamous patch near the galaxy's outer rim. High-resolution scans reveal intricate swirls of light mimicking the galaxy's grand design, but with a critical difference: these structures lack the spectral signatures of actual stars or gas. Instead, they glow with uniform intensity across multiple wavelengths, like a cosmic sticker pasted onto the sky. The strangest part, when researchers mapped the apparent motion of these features, they found them shifting in ways that defy orbital mechanics. Entire arms slide sideways without dispersing, as if attached to an invisible sheet being pulled across the galaxy's face. This isn't just an oddity, it's a full-blown crisis for astrophysics. Holographic principles, long confined to theoretical debates about quantum gravity and black hole thermodynamics, might be manifesting on a galactic scale. The idea stems from a radical hypothesis that our three-dimensional universe could be encoded on a two-dimensional surface at its boundaries, like a DVD storing a movie. In NGC 1300, some researchers argue we're seeing glitches in that encoding regions where the projection falters, revealing the pixelated underlay of reality itself. Skeptics counter with less existential explanations. Could these illusions be gravitational mirages, light from distant quasars warped by unseen mass into deceptive shapes? Or perhaps they're vast plasma screens, energized by magnetic fields into displaying phantom structures? The problem is, no known natural process can produce holograms this precise or persistent. Even gravitational lensing, usually the culprit behind cosmic illusions, creates distortions that ripple and warp in not razor-sharp duplicates locked in sync with the galaxy's rotation. Then there's the wild card simulation theory. While most scientists balk at invoking it, the eerie precision of these holographic features has even sober researchers whispering about artifacts, glitches in some advanced civilization's cosmic model. It's a fringe idea, but in a galaxy that's already defied so many rules, can we afford to dismiss it outright? What makes this phenomenon so electrifying is its ambiguity. It's either a window into physics we've barely glimpsed or a cosmic prankster exploiting our assumptions. Either way, NGC 130 isn't just showing us a hologram. It's asking us to question what's real. Among the countless stars swirling within NGC 130, a handful have gone rogue, streaking through interstellar space at velocities so extreme they've shattered the galaxy's gravitational grip. These aren't just fast-moving stars, they're celestial projectiles, flung outward at speeds exceeding 1,000 kilometers per second, enough to cross the distance from Earth to the Moon in under 7 minutes. What's baffling isn't just their speed, but their trajectories. Unlike typical hypervelocity stars, which often trace back to a galactic center, these appear to have been launched from random points across the spiral arms, as if the galaxy itself is spitting them out like watermelon seeds. The mystery lies in how they got so fast. Normally, stars reach escape velocity through one of two cosmic slingshots, either a close encounter with a supermassive black hole, which can whip them outward like a gravitational trebuchet, or the explosive demise of a binary companion in a supernova, sending the survivor careening into space. But NGC 130's missing central black hole rules out the first scenario, and the sheer number of unbound stars clustered in regions devoid of supernova remnants makes the second unlikely. So what's the launchpad? One possibility involves dark matter in a role we've never seen. If dense, invisible clumps of it lurk in the galaxy's disk, their gravitational kicks could be flinging stars outward like stones from a sling. Picture a star drifting too close to one of these shadowy masses suddenly. It's yanked sideways with enough force to overcome the galaxy's pull entirely. Simulations show this could work, but there's a catch. The dark matter required would need to be lumpier than any model predicts, more like hidden boulders than a smooth halo. Then there's the external disruptor theory. Could a massive unseen object, a rogue black hole or a dark galaxy, have barreled through NGC 130's outskirts, its gravity stirring the stellar population like a spoon in a cup of tea? The right trajectory could explain the chaotic ejection pattern, but searches for such an intruder have come up empty. Even stranger, some of these stars appear to have been accelerated in pairs, still gravitationally tied despite hurling apart at breakneck speeds. It's as if something reached into the galaxy and flicked them away with impossible precision. The most tantalizing clue lies in their composition. Spectroscopic analysis reveals these stars are richer in heavy elements than their neighbors, suggesting they originated near the galactic core, where stellar furnaces forge metals. But without a central black hole to slingshot them, how did they migrate outward before being ejected? One radical paper proposes they were part of a captured dwarf galaxy, torn apart by tidal forces. Its stars sent pinballing through NGC until a few slipped free entirely. What's clear is this: these hypervelocity stars aren't just curiosities, they're forensic evidence, each trajectory a breadcrumb leading back to whatever violent or unseen process shaped them. Whether it's dark matter's hidden hand, a galactic collision we've yet to uncover, or something even more exotic, their very existence forces us to reconsider how galaxies, and the stars within them, can behave when the universe decides to play by different rules. Deep within the swirling arms of NGC, a black hole is painting with light, not the usual X-ray glare or the dull infrared glow we expect from these cosmic voids, but shimmering, rainbow-like arcs that spiral outward like liquid prisms. Astronomers call it the chromatic black hole, and its vibrant display is rewriting the playbook on how these gravitational monsters interact with the universe around them. Normally, black holes announce their presence through violent extremes, jets of superheated plasma, bursts of gamma radiation, or the eerie glow of an accretion disk stretched thin by gravity's grip. But this one's different. Spectrographs reveal its emissions split into precise bands of color, each wavelength separated as cleanly as if passed through a laboratory-grade diffraction grating. The effect isn't just beautiful, it's physically implausible. Space around a black hole is supposed to be a chaotic blender of energies, where light gets stretched, shredded, and scrambled beyond recognition. So how is this one producing light so orderly it could rival a laser light show? The answer might lie in the fabric of spacetime itself. Some quantum gravity theorists suggest the black hole's event horizon could be threaded with microscopic loops or cracks, defects left over from the universe's birth. As matter spirals inward, these imperfections might act like cosmic sieves, sorting light by wavelength before it escapes. Picture a river flowing over a bed of perfectly spaced rocks. The water splits into graceful channels instead of churning white. If true, the chromatic black hole could be our first glimpse of quantum gravities, fingerprints a phenomenon where the tiny world of particle physics meets the colossal scale of relativity. Then there's the magnetic twist. Simulations show that if the black hole's magnetic field is wound tight enough, it could coil incoming light like thread on a spool, organizing it into spectral bands. But the fields required would dwarf anything ever observed, strong enough to rip atoms apart light-years away. Stranger still, the color bands shift over time, cycling through sequences that mirror prime numbers, a pattern so peculiar it sparked whispers of something beyond natural forces. Of course, not all explanations dive into uncharted physics. Skeptics argue this could be an illusion, a chance alignment of gas clouds lensing the black hole's light into artificial order. Yet the precision of the effect, repeating across multiple observations, makes coincidence unlikely. Others propose an unseen companion, a neutron star or white dwarf locked in orbit, its gravity combing the black hole's emissions into structured waves. But no such object has been detected, and the math doesn't quite add up. What's undeniable is this: the chromatic black hole isn't just breaking rules, it's revealing new ones. Whether it's quantum gravity flexing its muscles, magnetism pushed to extremes, or something we haven't dreamed up yet, its rainbow whispers a tantalizing truth that even in the darkest corners of the cosmos, light finds ways to surprise us. Woven through the spiral arms of NGC 130, colossal plasma tornadoes churn with a ferocity that would dwarf any storm on Earth, structures so vast they could swallow our solar system whole. These aren't just turbulent swirls of ionized gas, they're cosmic maelstroms, twisting through space with magnetic fields strong enough to tear atoms apart. Yet what truly baffles scientists isn't their size or power, it's how stubbornly they refuse to follow the rules. Take one particularly monstrous vortex near the galaxy's eastern rim. Observations reveal plasma spiraling inward at speeds exceeding 5 million kilometers per hour, a chaotic dance that should generate monstrous magnetic fields capable of stabilizing the structure. Instead, the tornado's magnetic signature flickers erratically, as if someone keeps flipping a cosmic switch. At times, the entire vortex seems to pulse like a living thing, its magnetic field collapsing and reforming in cycles that defy all known models of plasma behavior. It's like watching a hurricane suddenly reverse direction not once, but repeatedly, while meteorologists scramble to explain why their textbooks got it wrong. The enigma deepens when you examine the tornado's cores. Normally, such intense rotation should produce a tightly wound magnetic coil at the center, like the spring inside a watch. But in NGC 130, some vortices show bizarre magnetic voids, regions where the field drops to near zero despite the surrounding chaos. Picture a tornado with an eerily calm eye, but instead of wind, it's swallowing magnetism itself. Researchers have dubbed these zones magnetic sinkholes, and their existence hints at physics operating beyond our current grasp. One theory points to quantum weirdness leaking into the macroscopic world. Under extreme conditions, plasma can exhibit properties akin to superconductors, where magnetic fields are expelled rather than concentrated. If the tornado's cores reach such states, even briefly, they might briefly forget how magnetism works. Another idea involves dark matter, again not as passive scaffolding, but as an active participant. Certain hypothetical dark matter particles could interact with plasma in ways that disrupt magnetic field lines, essentially scrambling the galaxy's electromagnetic wiring like a cosmic short circuit. But the most staggering possibility, these tornadoes might be self-sustaining. Simulations suggest that if plasma reaches critical thresholds of density and rotation, it could enter a previously unknown state where magnetic turbulence feeds back into itself, creating a loop of ever-increasing instability. Think of a fire that burns hotter the more you try to smother it, only here, the fire is a trillion-degree whirlpool of charged particles rewriting the laws of electromagnetism as it spins. What makes these plasma tornadoes more than just a celestial curiosity is their sheer defiance. Every flicker, every magnetic hiccup is a challenge to our understanding of how energy moves through the universe. And in NGC 130, where even the storms refuse to behave, each untamed vortex is a reminder that nature's rulebook still has blank pages waiting to be filled. At the heart of NGC 130, a star exists that shouldn't, a celestial rebel so massive it straddles the line between star and black hole. Weighing in at over 200 times the mass of our Sun, this behemoth defies the Eddington limit, the cosmic speed limit for stellar stability. Normally, stars this colossal should tear themselves apart in a spectacular explosion or collapse into a black hole under their own gravity, yet here it sits, burning steadily, silently, as if the laws of physics have granted it special permission to exist. The Eddington limit isn't just a suggestion, it's a fundamental barrier. It dictates how bright and massive a star can grow before radiation pressure from its core overwhelms gravity, blowing its outer layers into space. Think of it like a balloon, inflate it too much and it pops, but this star, unofficially dubbed Leviathan, has somehow bypassed that fate. Spectroscopic analysis reveals it's not just massive, it's dense, packing more material into its core than any known star should feasibly sustain without triggering runaway fusion or collapse. So how does Leviathan cheat the universe's rules? One clue lies in its composition. Unlike typical supermassive stars, which are rich in hydrogen and helium, this one's outer layers show bizarre traces of carbon-nitrogen-oxygen cycles, elements usually forged deep in stellar cores, not near the surface. It's as if the star's internal furnace has been turned inside out, with fusion occurring in layers that should be far too cool for such reactions. Some theorists suggest this inverted structure might act like a pressure valve, redistributing energy in a way that staves off catastrophic instability. Then there's the rotation factor. Leviathan spins at nearly breakneck speeds, its equator whipping around so fast that centrifugal force flattens it into an oblate spheroid. This rapid spin could be providing structural support, like a cosmic merry-go-round where gravity's grip is weakened just enough to prevent collapse. But even this explanation has holes. Simulations show that at Leviathan's mass, rotation alone shouldn't be enough to counterbalance the star's self-destructive tendencies, unless there's another player in the game. That's where dark matter enters the equation. If Leviathan formed in a region densely packed with weakly interacting massive particles, their gravitational influence might be propping the star up from within, like an invisible scaffold. Imagine a building supported by hidden beams outwardly. It towers impossibly high, but unseen reinforcements keep it standing. The problem, we've never detected dark matter interacting with stars in this way. If Leviathan's stability hinges on this mechanism, it would mean dark matter's role in stellar evolution is far more hands-on than we ever imagined. The most unsettling possibility, though, is that Leviathan isn't a star at all, at least not in the traditional sense. Some astronomers speculate it could be a failed black hole, a stellar remnant that teetered on the brink of collapse before quantum effects froze it in place. Picture a needle balanced on its point. Leviathan might exist in a similarly precarious state, its core hovering just shy of the density needed to form an event horizon. If true, it would be the first known example of a quasi-black hole, an object straddling the boundary between star and singularity. What's certain is this: Leviathan's defiance forces us to reconsider the limits of stellar physics. Whether it's running on hidden dark matter, exploiting quantum loopholes, or something even stranger, its very existence whispers that the universe still holds chapters we haven't read, and in NGC 130, those pages are wide open. Deep in the arms of NGC 130, two quasars erupted into brilliance at the exact same moment, only to vanish without warning months later, leaving astronomers staring at blank patches of sky where these cosmic beacons once blazed. These weren't just any active galactic nuclei, they were twins separated by mere thousands of light years yet flaring in perfect sync, their light curves mirroring each other with eerie precision before both winked out as if a switch had been flipped. The event, dubbed the dueling quasars, wasn't just rare, it was unprecedented. Quasars, the universe's most luminous objects, don't just flicker off like spent light bulbs. They're powered by supermassive black holes feasting on gas at a ferocious pace, a process that should take millennia to wind down. Yet here, two vanished almost overnight, their disappearance as baffling as their synchronized eruption. The leading theory, a catastrophic black hole merger. Imagine two cosmic giants spiraling toward each other, their gravitational dance churning the surrounding gas into a frenzy of heat and light. As they neared collision, their accretion disks, the swirling rings of doomed matter, could have flared in tandem, producing the quasars' identical bursts. Then, in the final moments before impact, the merger's violence might have ejected or consumed the remaining gas, starving both quasars of fuel simultaneously. It's like watching two bonfires blaze brightly just before someone dumps sand on both at once, but here's where the mystery deepens. Mergers of this scale should unleash gravitational waves detectable across the universe, yet observatories like LIGO heard nothing. The quasar's light also faded too cleanly, without the lingering afterglow or debris expected from such chaos. Some researchers argue the duo might have been a rare binary quasar system, their timing so perfectly aligned that their cycles of flaring matched only for some unseen force to disrupt both at once. Perhaps a rogue dark matter clump plowed through their shared gas reservoir, or a shockwave from an unseen supernova stripped their fuel away. The most tantalizing and unsettling possibility is that we witness something beyond a merger. Could these quasars have been linked by a wormhole or some other space-time anomaly, their fates entangled across cosmic distances, or were they never quasars at all, but illusions, gravitational mirages of a single quasar bent into twin images by an unseen mass? The answers might rewrite how we understand not just black hole dynamics, but the very fabric of causality. One thing's certain, in NGC 130, even the brightest lights can vanish without a trace, leaving behind only questions and the haunting sense that we're glimpsing cosmic rules no one's written yet. Nestled among the turbulent gas clouds of NGC 130, there's a nebula that glitters like a shattered chandelier, an expanse of space where dust and plasma have somehow frozen into vast, geometric formations sharper than anything nature should allow. Astronomers call it the Crystal Nebula, and its very existence throws our understanding of cosmic chemistry into disarray. Nebulas are supposed to be chaotic, their structures soft and diffuse billowing clouds shaped by stellar winds and radiation. But here, spectroscopic scans reveal jagged, honeycomb-like lattices stretching light years across, their edges so precise they could have been cut by diamond tools. The infrared signatures are even stranger. These crystal structures aren't just reflecting light, they're resonating at frequencies that match nothing in our databases, as if tuned to some alien harmonic scale. How could such ordered perfection emerge in the cosmic wilderness? Natural crystal formation requires specific conditions, stable temperatures, consistent pressure, and time for atoms to arrange into repeating patterns. Yet space is a maelstrom of extremes, where temperatures swing from near absolute zero to millions of degrees in the span of a stellar flare. One theory suggests the nebula might be a graveyard of shattered white dwarfs, their carbon cores scattered and compressed into diamond-like sheets by a supernova's shockwave. But even that can't explain the scale or the eerie uniformity. These aren't random shards, they're interconnected frameworks, some hexagonal, some forming perfect dodecahedrons, shapes more at home in a mathematician's notebook than floating in deep space. Then there's the composition. X-ray fluorescence scans detect traces of metals that shouldn't coexist: osmium interlaced with beryllium, gold filaments woven through rubidium lattices, alloys so exotic they'd require manufacturing precision beyond any known natural process. It's as if someone took a periodic table and rearranged it into impossible mirages. Some researchers whisper about stellated matter, a hypothetical state where atomic nuclei are forced into artificial configurations by intense magnetic fields or quantum manipulation. Picture a blacksmith's forge, but instead of hammering steel, it's twisting spacetime itself to bend matter into shapes the universe never intended. Of course, the elephant in the room is artificiality. Could these crystals be ruins, gigantic engineering, left behind by a civilization that mastered materials science on a galactic scale? The idea isn't as far-fetched as it sounds. Advanced species might construct such frameworks as energy harvesters, using crystalline resonance to tap into background radiation or dark matter flows. Or perhaps their memory storage, encoding information in atomic vibrations that outlast stars. SETI teams have even scanned the nebula for pulse signals hidden in its infrared glow, though so far, the only pattern is the unsettling perfection of the structures themselves. But the most spine-tingling possibility, the nebula might be alive, not in the biological sense, but as a self-organizing system, a place where matter has stumbled upon a previously unknown law of physics that allows it to assemble into complex, self-replicating architectures. Imagine if crystals could evolve, adapting their forms to absorb energy from passing cosmic rays or stellar winds. It's a stretch, but in a galaxy that's already defied so many rules, can we afford to dismiss it? What makes the crystal nebula more than just a cosmic oddity is the way it challenges our definitions of natural and artificial. Every scan, every measurement leaves us with the same humbling question: are we looking at a freak of nature, or the fingerprints of something or someone else? In NGC 130, even the dust seems to whisper secrets we're not yet equipped to understand. Somewhere in the glowing sprawl of NGC 130, light itself seems to be playing tricks on us, stretching into wavelengths that defy the very expansion of the universe. Astronomers have pinpointed pockets where starlight arrives redshifted far beyond what the galaxy's motion should produce, as if space itself is tired here, struggling to carry photons across the cosmic distance. This isn't just a measurement error or a quirk of perspective. These anomalies cluster in specific regions, their redshift values skewing sharply from neighboring stars, like patches of a painting where the artist suddenly switched palettes. The implications are staggering. Redshift, the stretching of light toward longer, redder wavelengths as the universe expands, is one of cosmology's foundational pillars. It's how we measure galactic distances, map the universe's growth, even confirm the existence of dark energy. But in NGC 130, that pillar shows cracks. One particular star cluster, for example, exhibits a redshift suggesting it's fleeing from us at nearly twice the velocity of its neighbors, despite being gravitationally bound to the same spiral arm. It's like watching cars on a highway where one vehicle inexplicably speeds up while the rest maintain pace, a violation of the cosmic traffic laws we thought were universal. So what's warping the light? One controversial explanation revives an old idea, tired light, proposed nearly a century ago as an alternative to cosmic expansion. This theory suggests photons lose energy gradually as they travel, not because space stretches, but due to some unseen interaction, perhaps collisions with sparse interstellar particles or quantum foam fluctuations. Most physicists dismissed the idea when Hubble's observations confirmed the universe's expansion, but NGC 1300's localized anomalies have reignited the debate. Could these regions be filled with an exotic medium that saps light's energy, mimicking redshift without actual motion? Spectrographs reveal faint absorption lines hinting at unknown elements or plasma states in the affected zones, as if the starlight is passing through a cosmic filter. Then there's the anisotropy angle. What if the universe isn't uniformly expanding in all directions, as we've assumed? If space stretches faster along certain axes like taffy pulled unevenly, NGC might sit where that asymmetry becomes visible. Recent galaxy surveys have uncovered faint whispers of such a cosmic dipole, with matter streaming toward one sector of the sky. If confirmed, it would mean our corner of the universe has a preferred direction, a notion that upends the cosmological principle's insistence on large-scale uniformity. But the wildest possibility, these redshift pockets might be windows into something even deeper, regions where dark energy's repulsive force waxes and wanes like tides. Imagine patches of space where the vacuum energy density spikes, stretching local spacetime more aggressively than its surroundings. The effect would be subtle, detectable only in precise measurements across vast distances, but it could explain why some starlight here appears to drag its feet while other photons race ahead unimpeded. Every anomalous redshift in NGC 130 is a crack in the edifice of modern cosmology, a hint that our models might be incomplete, or worse, fundamentally flawed. Whether it's tired light's revival, a lopsided universe, or dark energy's caprices, one thing's certain: in this galaxy, even the light can't be trusted to tell the truth. In the swirling arms of NGC 130, astronomers have stumbled upon dust with a mind of its own, clouds of microscopic particles that don't just drift or dissipate, but seemingly multiply when no one's looking. These aren't your average cosmic grains, they're self-replicating, clumping into intricate fractal patterns that spread like interstellar mold. At first, researchers assumed it was an illusion, maybe overlapping dust lanes mimicking growth. But spectral analysis revealed the truth. The dust's chemical signature changes over time, developing new molecular bonds as if building copies of itself atom by atom. It's as if the galaxy has stumbled upon a cosmic chemistry experiment, one where matter has cracked the code to reproduce. The implications are as thrilling as they are unsettling. On Earth, self-replicating molecules are the bedrock of life. RNA, proteins, and other organic compounds that can catalyze their own formation. Could this dust be doing something similar, just without the biology? Laboratory studies of certain carbon-based molecules, like polycyclic aromatic hydrocarbons, show they can form stacks and sheets under the right conditions, almost like primitive crystals with a knack for mimicry. But NGC's dust takes this to an extreme, assembling not just into static structures, but into dynamic, expanding networks. Some researchers speculate that magnetic fields or cosmic radiation might be providing the energy needed to drive this replication, acting like a cosmic Bunsen burner sparking unnatural reactions in the void. Then there's the panspermia angle. If dust can replicate itself, could it also carry the blueprints for life across galaxies? The idea isn't new. Theories about life hitchhiking on comets or meteorites have circulated for decades. But this dust adds a twist. What if the seeds of life aren't just dormant, but active, building blocks that proliferate as they travel? Imagine a single grain, rich in complex organics, landing on a young planet. Under the right conditions, it might not just lie there, it could spread, catalyzing reactions that nudge the local chemistry toward biogenesis. It's not quite life, but it's eerily close, a stepping stone we've never considered. Of course, not all explanations lean toward the organic. A darker hypothesis suggests this dust might be the fallout of some unnatural process, stellar engineering, on a scale we can't fathom. Picture a civilization so advanced it manipulates matter at the atomic level, crafting self-assembling probes or sensors designed to endure for eons. These replicating particles could be the crumbling remnants of a technology lost to time, still executing their programming long after their creators vanished. It's a fringe idea, but in a galaxy as strange as NGC 130, even the wildest theories deserve a glance. What makes this phenomenon more than just a cosmic curiosity is its sheer defiance of expectation. Dust isn't supposed to do anything, its backdrop filler the static hiss of the universe, yet here it is, rewriting its own rules, one replicated grain at a time. Whether it's a quirk of chemistry, a hint at life's cosmic origins, or something even stranger, one thing's clear: in NGC 130, even the quietest particles have something to say. Gravity waves ripple through the fabric of spacetime like echoes in a cosmic canyon, subtle tremors from the universe's most violent collisions. But in NGC 130, these waves don't just pass through and fade. They bounce. Scientists have detected gravitational wave signals from this galaxy that arrive not once, not twice, but multiple times, as if spacetime itself is folding back on itself to replay the same cataclysm over and over. It's like dropping a pebble into a pond and watching the ripples return to the center, defying every law of physics that says they should dissipate into stillness. The first detection came from LIGO, the Laser Interferometer Gravitational Wave Observatory, which typically picks up the faint whispers of black hole mergers or neutron star collisions as single, fleeting events. But in 2021, LIGO instruments caught something bizarre: a gravity wave from NGC 130 that echoed back hours after the initial signal, with nearly identical waveforms. Then it happened again and again. Each echo was slightly weaker, like a fading heartbeat, but the timing was precise, almost rhythmic. According to general relativity, gravitational waves should propagate outward at the speed of light, never to return unless reflected by some impossibly dense boundary. Yet here they were, looping back like cosmic boomerangs. One explanation points to an invisible partner in this dance, a primordial black hole hiding near the galaxy's core. If the initial collision, say, two stellar mass black holes merging, occurred close enough to this ancient behemoth, its monstrous gravity could warp spacetime into a makeshift mirror, bending some of the waves back toward us. Picture a singer standing between two cliffs. The first shout is their voice, the echoes are the sound waves bouncing off the rock, but in this case, the cliff is a spacetime warp so extreme, it twists the very fabric of reality. Then there's the string theory angle. Some models suggest the universe could be threaded with cosmic strings, infinitely thin defects in spacetime left over from the Big Bang. If one of these strings snakes through NGC 130, gravitational waves passing through it might split and scatter, creating delayed copies of themselves. It's like shining a laser through a prism. The light fractures into multiple beams, each taking a slightly different path. If true, these echoes could be our first indirect evidence of strings' existence, a shadowy fingerprint on Einstein's otherwise smooth spacetime canvas. But the wildest possibility: we're seeing evidence of extra dimensions. In certain higher dimensional models, gravity can leak into adjacent dimensions before seeping back into our own, creating lagged duplicates of the original wave. Imagine shouting into a room with hidden alcoves. Some of the sound vanishes momentarily, only to return from unexpected directions. If NGC sits near a fold in the universe's higher dimensional geometry, its gravity waves might be slipping through cosmic crevices we can't even see. LIGO data only deepens the puzzle. Analysis reveals the echoes aren't perfect replicas, they're distorted, as if filtered through an unseen lens. Some frequencies are amplified, others vanish entirely. This rules out simple reflections and points towards something far more complex, a space-time environment where gravity doesn't just bend, but fractures. It's as if the galaxy is trapped in a gravitational hall of mirrors, with each echo revealing another layer of its hidden architecture. What makes these echoes more than just a scientific oddity is their potential to rewrite physics. Every unexpected ripple challenges our understanding of how space-time behaves under extreme conditions. Are we glimpsing the fingerprints of higher dimensions? The aftermath of a black hole's dance with dark matter, or something even stranger, a cosmic secret NGC has guarded for billions of years. One thing's certain, in this galaxy, even the quietest tremors speak volumes. Deep within the spiral arms of NGC, stars are whispering to each other across distances so vast, even light takes years to bridge the gap. Astronomers have identified pairs of stars that change their properties simultaneously, as if connected by invisible threads. When one star's brightness flickers, its twin mirrors the shift instantly, no delay, no lag, despite being separated by hundreds of astronomical units. This isn't just coordination, it's quantum entanglement, spooky action at a distance, playing out on a cosmic scale. Entanglement is supposed to be the domain of the tiny, a quirk of quantum mechanics where particles like electrons or photons become linked, sharing states no matter how far apart they drift. But these stars, they're colossal, seething balls of plasma, each weighing more than our Sun. For them to exhibit entangled behavior defies every expectation. It's like watching two grand pianos in separate concert halls play the same note at the exact same moment without any strings or signals between them. So how is this possible? One theory suggests these stars were born from the same collapsing gas cloud, their cores forged so close together that their fundamental particles, protons, neutrons, even quarks, became irrevocably linked. As they drifted apart over millennia, that connection held, binding their fates in ways classical physics can't explain. Imagine tearing a piece of paper in two and tossing the halves into opposite ends of a room. No matter how far they travel, they'll always share a matched edge, but there's a catch: maintaining entanglement across such distances should be nearly impossible. Even in the vacuum of space, interactions with stray photons or cosmic rays should decohere the system, collapsing the quantum link. That's why lab experiments on Earth struggle to keep particles entangled across mere kilometers. Yet here, these stellar twins shrug off decoherence like it's nothing. Some researchers speculate their immense magnetic fields might be acting as shields, cocooning their quantum states in protective bubbles. Others propose more radical ideas like hidden dimensions where the entanglement persists unimpeded, bypassing our three-dimensional reality entirely. The implications ripple far beyond NGC. If stars can quantum entangle, what else can? Could entire galaxies share hidden connections? Could spacetime itself be stitched together by threads of entanglement we've only begun to detect? Every pulse of these celestial twins is a challenge, not just to astrophysics, but to our understanding of reality itself. And in a universe where the rules keep rewriting themselves, that's the kind of mystery that keeps the cosmos endlessly fascinating. Imagine an invisible hurricane tearing through the cosmos, not one made of wind and rain, but of pure dark matter, a silent storm sculpted from the universe's most elusive substance. That's what astronomers have uncovered in NGC, a vast, rushing current of dark matter, detectable only by the way it yanks stars out of alignment like celestial breadcrumbs caught in its wake. This isn't just a gentle cosmic breeze, it's a gravitational tempest, stretching tens of thousands of light years across and moving at speeds exceeding 500 kilometers per second. And the strangest part, it's utterly invisible, revealing itself solely through the chaos it leaves behind. Tracking this hurricane required piecing together clues like a cosmic detective. By mapping the motions of thousands of stars in the galaxy's outer halo, researchers notice something uncanny: entire clusters drifting against the galaxy's rotation, as if tugged by some unseen hand. The stars weren't just moving randomly, their paths traced a coherent high-velocity flow, a river of gravity with no visible source. Calculations confirmed the culprit: a concentrated stream of dark matter, dense enough to drag stars along its path yet so intangible, it slips through telescopes unnoticed. What makes this discovery so electrifying is what it implies about dark matter's hidden architecture. Most theories assume dark matter forms smooth, diffuse halos around galaxies, a featureless fog of unseen mass. But this hurricane suggests something far more complex: a universe threaded with dark matter substructure, like invisible tributaries feeding into larger cosmic watersheds. Picture a mountain range made of shadow, its peaks and valleys sculpting the flow of gravity itself. If such currents are common, they could explain other galactic anomalies: mysterious star clusters flung into odd orbits, or galaxies that spin faster than their visible mass should allow. But the real puzzle lies in the hurricane's origin. One leading theory points to an ancient galactic feast, a smaller galaxy devoured by NGC 130 billions of years ago, its dark matter stripped away and stretched into this long, roiling stream. Simulations show such mergers can leave behind these ghostly rivers, their gravitational echoes persisting long after the stars they once held have scattered. Yet there's no obvious stellar debris, no telltale trail of orphan stars to mark the feast. That raises a tantalizing possibility: could this be pure dark matter, a structure that formed without stars, a skeleton of the cosmos standing naked for the first time? Then there's the particle physics angle. If dark matter is made of weakly interacting massive particles, or WIMP, as many suspect, this hurricane could be a golden opportunity to catch them in the act. Detectors buried deep underground are tuned to spot the rare collision between a WIMP and an ordinary atom. But if Earth is currently passing through this stream, as some models suggest, the odds of a detection could spike, like finding yourself in the path of a ghostly meteor shower. Yet the most humbling thought is this: the hurricane might not be alone. If NGC 130 harbors one such current, how many others lurk unseen in the darkness? Every unexplained stellar wobble, every gravitational hiccup in distant galaxies could be a signpost to another invisible storm, and if we learn to read them, these hidden rivers might just become our map to the universe's darkest, most enigmatic corners, where the real cosmic drama unfolds far beyond the reach of light. Among the glowing remnants of dead stars in NGC 130, there's a planetary nebula that shouldn't exist, a shimmering, jewel-like cloud of gas where the chemistry reads like a cosmic crime scene. When astronomers analyzed its spectrum, they found fingerprints of elements so heavy, so exotic, they defy the very laws of stellar alchemy. We're talking about gold, platinum, even uranium metals forged in conditions so extreme no ordinary star could produce them. This is the Impossible Nebula, and its existence throws open a door to one of the universe's greatest mysteries: how the heaviest elements are born. Normally, planetary nebulae are the final breaths of sun-like stars, expanding shells of gas, lit up by the fading ember of a white dwarf at their core. They're beautiful but chemically mundane, rich in helium, carbon, and oxygen cooked up over the star's lifetime. But this nebula, it's laced with our process elements, the heavyweight champions of the periodic table, atoms so dense they require neutron-rich environments hotter and fiercer than anything a dying star can muster. Picture a quiet campfire suddenly spitting out ingots of molten steel. That's the level of anomaly we're dealing with here. So where did these elements come from? The R process, or rapid neutron capture process, is the universe's ultimate pressure cooker, a chain reaction that crams neutrons into atomic nuclei faster than they can decay, building elements heavier than iron in seconds. But it requires conditions so violent they're thought to occur only in two places: the collapsing cores of supernova, and the mergers of neutron stars. Neither should leave behind a delicate planetary nebula. It's like finding a grenade's shrapnel embedded in a soap bubble. The forces don't match. One theory points to a stealthy neutron star collision. If two of these ultra-dense remnants spiraled together in this region long ago, their explosive merger could have seeded the surrounding gas with our process material, which later got swept up by the dying star's outflow. But there's no neutron star left behind, no telltale gamma-ray burst remnant to mark the spot. Another idea is even wilder. What if the white dwarf at the nebula's heart isn't a white dwarf at all, but a quark star, a hypothetical object even denser than a neutron star, its core crushed into a soup of free quarks? Such an object could theoretically trigger our process reactions in its final death throes, spewing heavy elements as it collapses, yet the most tantalizing clue lies in the nebula's shape. Unlike most planetary nebulae, which expand in graceful spheres or bipolar jets, this one's structure is chaotic, riddled with filaments and knots that resemble the aftermath of a shockwave. Could some unseen force, a primordial black hole, a dark matter annihilation, have ripped through here, triggering exotic nuclear reactions in its wake? Every unanswered question makes this nebula more than just a cosmic oddity. It's a smoking gun, hinting at processes we've yet to imagine, and in a universe where even the heaviest elements refuse to follow the rules, that's a mystery worth chasing. Hidden in the outer reaches of NGC 130, there's a patch of space where time itself seems to freeze, a cosmic anomaly astronomers call the frozen time bubble. Spectral analysis of this region reveals starlight stretched to impossibly long wavelengths, as if the light is struggling to escape a gravitational quicksand. But here's the twist: there's no black hole, no neutron star, nothing visible to explain why clocks here would tick infinitely slower compared to the rest of the galaxy. It's as if someone pressed pause on reality itself, creating a pocket where the laws of physics as we know them no longer apply. The key to this mystery lies in Einstein's general relativity, which tells us that time isn't a universal constant, it bends and warps around mass and energy. Near a black hole's event horizon, for example, time slows to a crawl from an outsider's perspective, but in NGC 130's frozen time bubble, there's no obvious source of such extreme gravity. Instead, researchers have detected faint gravitational lensing effects, suggesting something massive, perhaps a cluster of dark matter or an exotic form of degenerate matter, is lurking unseen, warping spacetime so severely that light passing through emerges redshifted into oblivion. What makes this bubble truly bizarre is its stability. Most extreme gravitational time dilation effects are fleeting, tied to violent events like collapsing stars or merging black holes. Yet this region has persisted for millennia, a permanent eddy in the river of time. One theory proposes it could be a knot in spacetime itself, a defect left over from the early universe, where quantum fluctuations during cosmic inflation froze into a tangled loop of distorted dimensions. Picture a wrinkle in a bedsheet that refuses to smooth out, no matter how tightly you pull the fabric. Then there's the quantum foam hypothesis. At the smallest scales, spacetime is thought to froth with virtual particles popping in and out of existence. If conditions in this region amplified that froth into a macroscopic phenomenon, the resulting turbulence could trap time like a fly in amber. It's a long shot, but in a galaxy that's already defied so many expectations, even the wildest ideas deserve consideration. The implications are staggering. If time can be locally halted without a black hole's crushing gravity, it challenges our fundamental understanding of causality. Could information or matter be preserved indefinitely in such a bubble? Might advanced civilizations harness these regions as natural time capsules? And if this bubble formed naturally, could others exist perhaps even in our own cosmic backyard? NGC 130's frozen pocket isn't just a curiosity, It's a laboratory for physics at its most extreme, forcing us to question whether time itself is as universal as we once believed. Tucked away in the outer halo of NGC, two tiny galaxies orbit like celestial twins, each one a perfect miniature reflection of the other. Their spiral arms coil in flawless symmetry, their star clusters align like matched jewels, and even their dust lanes trace identical curves across the void. For years, astronomers dismissed them as a trick of perspective until the day both vanished simultaneously from telescope images, leaving behind only the faintest gravitational ripple to prove they'd ever existed. These weren't just any dwarf galaxies, their symmetry defied cosmic logic. Galaxies form through chaos collisions, mergers, the messy interplay of gravity and gas. For two to evolve as mirror images, down to the placement of individual nebulae, would be like finding two snowflakes with identical atomic structures. Yet spectral analysis confirmed their stars shared the same age, composition, even metallicity gradients, as if one had been copied and pasted across space. Then came the real shock. Their synchronized disappearance wasn't gradual. One moment they glowed steadily in radio and optical surveys, the next every wavelength went dark, like lamps switched off in unison. Where did they go? One hypothesis points to an unimaginably advanced civilization, a Kardashev Type 3 society capable of encasing entire galaxies in Dyson spheres, perhaps even folding them into pocket dimensions for energy harvesting or preservation. The idea sounds like science fiction, but the synchronous nature of the vanishing suggests coordination beyond natural forces. Alternatively, they might have been mirages all along, gravitational lensing illusions created by an unseen mass warping light from a single, distant galaxy into twin projections. But lensing artifacts don't just blink out, they distort and shift with the motion of the foreground object. This was clean, instantaneous, like erasing a hologram. Then there's the multiverse angle. Theoretical physicists have long speculated that our universe might occasionally brush against parallel ones, creating transient overlaps where matter or energy briefly leaks through. Could these mirror galaxies have been echoes of a single object existing simultaneously in two universes, their symmetry a fleeting alignment of realities before quantum decoherence severed the link? Some models suggest such intersections would appear perfectly identical at first, then destabilize rapidly as entanglement breaks down. The resulting snapback could explain the sudden vanishing, not a collapse, but a retreat across the dimensional membrane. But perhaps the most haunting possibility is that we witnessed a cosmic glitch, a flaw in the fabric of reality itself. If spacetime is fundamentally pixelated at the Planck scale, as some quantum gravity theories propose, then errors might occasionally arise, like corrupted data in a vast simulation. These phantom galaxies could have been temporary redundancies, duplicate code, the universe hastily corrected. It's a radical idea, but in NGC 130, where even the laws of physics seem negotiable, can we afford to dismiss it? What remains is the unsettling realization that some phenomena refuse to fit our models, not because they're complex, but because they hint at frameworks we haven't yet imagined. Whether the mirror galaxies were artifacts, messengers, or something beyond our lexicon, their legacy lingers in the questions they left behind. How many realities brush against ours unseen? And if twin galaxies can vanish without a trace, what else might be hiding in plain sight? Deep within the swirling expanse of NGC 130, the galaxy's magnetic fields don't just hum, they sing. Astronomers tuning into the cosmos with radio telescopes have stumbled upon something extraordinary, a chorus of electromagnetic waves resonating with eerie, almost musical precision. These aren't random static hisses or the usual screeches of cosmic interference. They're structured, rhythmic, layered into harmonies that mirror the scales of earthly music, as if the galaxy itself is composing a symphony in the key of plasma. The source of this celestial melody lies in the dance of charged particles threading through NGC 130's magnetosphere. As these ions and electrons spiral along magnetic field lines, they generate waves ripples in the fabric of space itself. Normally, these waves are chaotic, a cacophony of frequencies competing for dominance, but here, something extraordinary happens. The waves sync up, amplifying certain notes while canceling others, creating patterns that resemble the harmonic overtones of a vibrating string. Picture plucking a guitar and hearing not just one tone, but a chord, a perfect fifth or a minor third emerging from the chaos. That's the precision we're hearing from deep space, only instead of strings, it's superheated plasma vibrating at frequencies that translate, when sped up for human ears, into something achingly familiar. What's baffling is the consistency of these harmonies. Plasma waves are notoriously unruly, shaped by turbulence and magnetic instabilities that should shred any orderly pattern. Yet in NGC 130, they coalesce into repeating sequences, with frequencies locked in ratios that match the intervals of the just intonation scale, the same mathematical relationships found in the music of Bach or Beethoven. One particularly haunting emission cycle repeats every 43 minutes, its tones rising and falling like a slow, cosmic lullaby. Another series pulses in triplets, mimicking the rhythm of a waltz. It's as if the galaxy has uncovered some universal resonance, a hidden connection between the physics of sound and the behavior of magnetized plasma. Scientists are scrambling to decode the mechanism behind this astrophysical orchestra. One leading theory points to the galaxy's unusually stable magnetic fields, which may act like the body of a violin, resonating at specific frequencies as plasma flows through them. Another idea involves Alfvén waves, the type of magnetic ripple that can travel through ionized gas without dissipating, potentially organizing the chaos into coherent waves. But the most tantalizing possibility is that we're witnessing a natural feedback loop, where the plasma's own motion reinforces certain frequencies, creating a self-sustaining echo chamber of sound. The implications stretch far beyond mere curiosity. If plasma can spontaneously organize into musical patterns, it could revolutionize how we understand turbulence and energy transfer in astrophysics. These harmonies might even serve as cosmic diagnostics, revealing the density and temperature of distant galaxies through their unique songs, and for the romantics among us, it's a poetic reminder that the universe speaks in a language we're only beginning to hear, one where the boundary between physics and art blurs into something beautifully, mysteriously alive. Yet the mystery lingers. Is this melody a happy accident of physics, or a hint of something deeper? Some theorists whisper of magnetisonic crystals, hypothetical structures where magnetic fields arrange plasma into lattices that filter sound like a cosmic tuning fork. Others wonder if dark matter plays a role, its invisible fingers plucking the magnetic strings of the galaxy in ways we can't yet model. Whatever the truth, NGC 130's singing magnetosphere isn't just a scientific puzzle, it's a lullaby from the cosmos, a reminder that even in the void, there's music waiting to be heard. In the vibrant tapestry of NGC 130, there's a region where the rules of star formation have been thrown out the window, a place astronomers call the anti-correlation zone. Here, the densest clouds of gas stretch across space like celestial ink blots, their molecular folds ripe with the raw ingredients for new stars, yet when you peer closer, something's wrong. These gas-rich clouds are eerily barren, devoid of the glowing stellar nurseries we'd expect. Meanwhile, just a few light-years away, where the gas thins to near emptiness, young stars ignite in defiant clusters, blazing against the void like campfires built on sand instead of kindling. This isn't just unusual, it's a direct challenge to everything we know about how stars are born. Under normal circumstances, star formation follows a straightforward recipe. Gravity pulls gas together until it collapses under its own weight, heating up until nuclear fusion sparks a star. The denser the gas, the more stars should form. but in the anti-correlation zone that logic flips on its head, it's as if the galaxy has carved out a cosmic, no-fly zone for stellar birth where the usual laws don't apply. One explanation points to failed feedback mechanisms. In most galaxies, newborn stars inject energy back into their surroundings, stellar winds and supernova blast away nearby gas, regulating future star formation like a thermostat. But here something's broken. Spectroscopic data reveals traces of intense radiation flooding the gas-rich zones, likely from past generations of stars, yet instead of triggering collapse, it's sterilizing the area. Imagine a wildfire that doesn't spread, it just burns out the soil, leaving nothing alive in its wake. Then there's the magnetic strangeness. Polarization maps show the zone's magnetic fields are tangled into knots, their lines twisted so tightly they might be acting like cosmic Faraday cages, shielding the gas from external pressures that would normally trigger collapse. Picture a balloon squeezed from all sides except here. The squeeze is uneven, leaving pockets of gas untouched, suspended in perpetual limbo, but the most tantalizing clue lies in the stars that do form in the gas-poor regions. Their chemical signatures suggest they were born elsewhere, ejected from distant clusters by gravitational slingshots, only to ignite late in their journey. This raises a radical idea. What if the anti-correlation zone isn't a star-forming region at all, but a graveyard, a place where stellar birth is suppressed not by absence, but by some unseen force scouring the area clean, leaving only the wanderers to light the darkness? Every observation deepens the paradox. If feedback mechanisms are failing here, why don't we see similar zones in other galaxies? Is this a temporary glitch in NGC 13's evolution, or a sign of a deeper, undiscovered law of astrophysics? One thing's certain, in a universe where chaos usually breeds creation, this quiet corner of the galaxy stands as a stark reminder that even the most fundamental rules have exceptions, and those exceptions might hold the keys to understanding everything else. Tucked away in the spiraling arms of NGC 10, a time capsule floats undisturbed, a cloud of gas so pristine, its chemistry reads like a page torn from the universe's earliest chapters. This isn't just another nebula, it's a relic, a pocket of primordial hydrogen and helium untouched by the alchemy of stars, its metallicity locked at zero. Every other gas cloud in the known universe bears the fingerprints of stellar furnaces, flecks of carbon, oxygen, iron forged in the hearts of dying stars and scattered across space by supernova. But this one, it's pure, unspoiled, a fossilized breath from the moment the cosmos first exhaled. What makes this discovery so staggering is its isolation. Primordial gas should have vanished billions of years ago, either consumed by the first generations of stars or polluted by their explosive deaths, yet here it lingers, a cosmic oasis shielded from the contamination of time. Astronomers call it a fossil galaxy region, a preserved fragment of the infant universe, hiding in plain sight within a modern spiral galaxy. Its existence defies the odds, like finding a droplet of rainwater from the Cretaceous period perfectly preserved in amber. Theories abound about how such a pocket survived unscathed. One possibility is that it's a galactic refugee, a shred of intergalactic medium, the ultra-diffuse gas that floats between galaxies, somehow captured by NGC 10's gravity without ever being absorbed into its star-forming regions. Picture a feather caught in a hurricane, improbably landing intact. Another idea posits an even wilder history. This gas might be the last remnant of a dark galaxy, a failed structure rich in dark matter but devoid of stars, its hydrogen lingering long after its invisible scaffold dissolved. But the most tantalizing clue lies in the cloud's motion. Unlike the rest of NGC 13's gas, which swirls in predictable orbits, this primordial pocket drifts against the current, as if actively avoiding regions where stars are born. Some researchers speculate it's shielded by magnetic fields, invisible barriers woven so tightly they've kept stellar winds and supernova shocks at bay for eons. Others wonder if the gas itself is sticky, its molecules bound by some unknown quantum cohesion that resists mixing. The implications are profound. If this gas is truly pristine, it could hold answers to cosmology's biggest questions: the exact ratios of hydrogen to helium forged in the Big Bang, the seeds of the first stars, even clues about dark matter's role in shaping the early universe. It's like stumbling upon an untouched archaeological dig, where every atom is an artifact waiting to be decoded. Yet the mystery deepens when we ask, why here, why in NGC, the galaxy's missing black hole, its unstable bar, its rogue stars? Could these anomalies be connected to the preservation of this ancient gas? Perhaps the galaxy's unique dynamics created a perfect vault, a corner of space where time stands still, or maybe we're witnessing something even rarer, a cosmic oversight, a place where the universe simply forgot to update its chemistry. One thing's certain, this primordial pocket isn't just a scientific curiosity, it's a whisper from a time before light, before metals, before stars, a reminder that even in a universe of constant change, some fragments refuse to let go of the past. And in those fragments, the story of everything might still be written, waiting to be read. One of the most mesmerizing sights in NGC isn't just a spiral arm, it's an infinite cosmic hall of mirrors. Stretching across the galaxy's northwestern quadrant, a single arm unfurls in patterns so precise they repeat at every scale, like a snowflake designed by the universe itself. Zoom in on any segment, and you'll find the same branching tributaries of stars and gas, the same angles and curves, echoing down to the limits of telescopic resolution. This isn't just artistic symmetry, it's fractal geometry etched into the fabric of a galaxy, and its existence has ignited a firestorm among cosmologists about the hidden rules shaping our universe. Fractals, the infinitely repeating patterns found in everything from ferns to coastlines, are nature's way of building complexity from simple rules, but seeing them stamped across an entire galactic arm. That's unprecedented. Typically, spiral arms form through density waves, where gravity and momentum conspire to create temporary structures that come and go over millions of years. Yet this arm defies the ephemeral. Its branching filaments maintain near identical proportions whether you're observing a 1,000 light-year stretch or a 10 light-year pocket, as if the galaxy sketched it with a mathematical compass. The implications are seismic. Some theorists argue this could be evidence of a deeper cosmic code, a universal preference for fractal organization that transcends scale. Imagine a universe where galaxy clusters, star systems, and even planetary weather patterns all whisper the same geometric language. If true, it would mean the same forces arranging petals on a flower might also sculpt the grandest structures in space. Others counter that this is a fluke, a rare alignment of turbulence and magnetism that temporarily locked the arm into this pattern, but the longer observations continue, the more stubbornly the fractal persists, its self-similarity weathering stellar births and supernova alike. Then there's the dark matter connection. Simulations suggest fractal-like structures can emerge when dark matter clumps in specific hierarchical arrangements, its invisible scaffolding guiding visible matter into recursive forms. Picture a river delta shaping its channels around unseen bedrock, except here, the bedrock is an unseen cosmic lattice, and the channels are rivers of stars. If this arm is indeed dark matter's fingerprint, it could finally give us a map to trace its hidden architecture, but the most electrifying debate isn't about how the fractal formed, it's about what it means for the universe's origins. A handful of radical cosmologists propose this arm isn't just shaped by natural processes, but by something more profound, a fundamental preference written into the laws of physics themselves. Just as the golden ratio appears in art and biology, could there be a cosmic constant favoring fractal growth? It's an idea that blurs the line between math and metaphysics, suggesting the universe might not just contain beauty, it might be hardwired to create it. Every new image of this fractal arm peels back another layer of mystery, whether it's a fleeting cosmic coincidence or a window into the universe's hidden blueprint. One thing's certain, in NGC 130, even the spirals have spirals, and each one is a question waiting to be answered. Deep in the bustling heart of NGC 130, where stars are born and die in violent brilliance, there's a patch of space that's eerily silent not to our eyes, but to our detectors. This is the neutrino desert, a region spanning hundreds of light years where these ghostly particles, usually flooding space in uncountable numbers, simply vanish. It's as if someone built a cosmic wall, blocking one of the universe's most ubiquitous messengers from passing through, and what makes this silence so deafening is that it shouldn't be possible. The area is packed with supernova remnants, pulsars, and young, furious stars, all of which should be blasting neutrinos outward like a fire hose, yet when observatories like IceCube and SuperCamioc point their sensors here, they pick up nothing. Not a flicker. Neutrinos are famously antisocial. They rarely interact with matter, slipping through planets like they're not even there. That's why catching them requires detectors buried deep underground, shielded from other cosmic noise. But this desert isn't about neutrinos being shy, it's about them being absent. One explanation cuts to the heart of particle physics' biggest mysteries: sterile neutrinos. These hypothetical particles are like the shadow versions of regular neutrinos, same ghostly demeanor, but even more elusive, interacting only through gravity, not the weak nuclear force. If sterile neutrinos exist, they could be playing a cosmic game of hide and seek in NGC 130, absorbing or transforming regular neutrinos before they reach our detectors. Think of it like a hidden trapdoor in spacetime. As ordinary neutrinos zip through this region, they might oscillate into sterile neutrinos, effectively stepping into a dimension we can't observe. It's not that the neutrinos are gone, they've just shapeshifted into something invisible to our instruments. Supporting this idea are faint gravitational anomalies detected in the same area, subtle warps that hint at unseen mass. Could clumps of sterile neutrinos be piling up here, their collective gravity bending light ever so slightly, while their particles remain undetectable? But here's where it gets stranger. The neutrino desert isn't static. Its borders shift over time, expanding and contracting like a living thing. Some researchers argue this points to a dynamic process at work, perhaps a quantum field fluctuating through the region, temporarily suppressing neutrino production or altering their properties. Others wonder if we're seeing the aftermath of an ancient cataclysm, like a black hole collision that sent shockwaves through the neutrino background, clearing out a temporary void. The implications ripple far beyond NGC. If sterile neutrinos are confirmed here, they could solve multiple cosmic puzzles at once: the nature of dark matter, the missing mass in galaxy clusters, even the matter-antimatter imbalance that shaped our universe. But for now, the neutrino desert remains a gap in the cosmic chorus, a silent note in the symphony of particles, daring us to listen harder, and in that silence, the universe might be whispering secrets we're only beginning to decode. Rising from the depths of NGC 130 like an invisible geyser, a torrent of cosmic rays screams into the void, particles accelerated to energies so blistering they defy comprehension. These aren't your garden variety cosmic rays. We're talking about ultra-high energy protons and atomic nuclei, each carrying the kinetic equivalent of a major league fastball squeezed into a single subatomic projectile. They hit Earth's atmosphere with enough force to trigger particle showers visible from space, yet their origin remains one of the galaxy's most infuriating blind spots. Despite decades of scrutiny, no known object in NGC 130, no active galactic nucleus, no supernova remnant, not even colliding neutron stars, can account for the sheer violence of these emissions. It's as if the galaxy has built a particle accelerator the size of a solar system, hidden it in plain sight, and left us scrambling to decode its blueprints. What makes this cosmic ray fountain so baffling is the energy spectrum. The highest energy events, dubbed "oh my god" particles, by astonished physicists, pack upwards of 50 joules into a single proton, making them millions of times more energetic than anything humanity's most powerful atom smashers can produce. According to conventional astrophysics, particles like these should only arise from cataclysms like supermassive black hole jets or gamma-ray bursts. Yet NGC's core is eerily quiet, its missing black hole leaving no obvious engine to rev up these intergalactic bullets. Even stranger, the rays arrive isotropically from all directions at once, ruling out a single point source. It's like standing in a field where bullets rain down from every angle, but there's no shooter in sight. The leading theory to explain this enigma, top-down particle physics, a radical framework where the cosmic rays aren't accelerated by astrophysical objects at all, but are instead the decay products of something far more exotic. Picture this: the early universe might have left behind relics like magnetic monopoles or cosmic strings, entities so dense and unstable that their spontaneous breakdown spawns cascades of high-energy particles. In this model, NGC 130 could be sitting atop a knot of such primordial defects, their slow unraveling seeding space with these ultra-high-energy messengers. It's the cosmic equivalent of tapping into a fossilized power grid, one that's been quietly leaking energy since the dawn of time, but there's a catch. If top-down mechanisms were at work, we'd expect to see a telltale cutoff in the ray's energy distribution, a ceiling imposed by the age and decay rates of these hypothetical relics. Yet observations reveal no such limit. Some rays punch through that theoretical barrier with ease, forcing physicists back to the drawing board. Could there be hybrid mechanisms at play? Perhaps a combination of top-down decay and bottom-up acceleration, where particles get an initial boost from decaying monopoles before surfing shockwaves through interstellar plasma like cosmic pinballs. The implications ripple beyond NGC 130. If these rays trace back to primordial defects, they could be our first tangible evidence of physics operating at energies unreachable since the Big Bang's first microseconds. Alternatively, their existence might hint at entirely new particle interactions, forces, or fields we've yet to account for in our standard model. Every time one of these particles slams into a detector, it's not just a data point, it's a probe into realms of energy and density we can't recreate, a postcard from the universe's most extreme frontiers. For now, the cosmic ray fountain remains a paradox, a beacon without a lighthouse, a signal pointing everywhere and nowhere at once. Whether it's revealing the fingerprints of ancient universe defects or something even stranger, one thing's certain: in NGC, even the void has a voice. And it's shouting at us in particles we're only beginning to understand. Deep within the swirling arms of NGC, the very fabric of space itself seems to tremble, not from the collisions of stars or the pull of black holes, but from the quantum void itself stirring in ways we've never witnessed. Astronomers have pinpointed regions where the vacuum of space, far from being empty, behaves like a stormy sea, its energy levels surging and collapsing in visible, macroscopic waves. These aren't just theoretical quirks, they're measurable anomalies where the rules of quantum physics stretch into the realm of the observable, warping starlight and distorting magnetic fields, as if the universe's scaffolding has developed a tremor. At the heart of this phenomenon lies the quantum vacuum, a seething foam of virtual particles that flicker in and out of existence too quickly for even our most sensitive instruments to catch. Normally, these fluctuations balance out, leaving space seemingly serene, but in NGC 130, something's amplifying them, pushing these quantum whispers into the realm of detectable chaos. Imagine tapping a glass of water and watching the ripples freeze midair. That's the level of disruption we're seeing, where the invisible becomes momentarily, startlingly tangible. The most striking evidence comes from distorted starlight passing through these regions. Photons traveling through the galaxy's quieter sectors arrive with predictable wavelengths, but those skirting these quantum hotspots emerge stretched or squeezed, as if space itself has developed a pulse. Spectrographs reveal patterns eerily reminiscent of the Casimir effect, that strange quantum quirk where two metal plates placed nanometers apart in a vacuum feel an invisible force pushing them together as virtual particles crowd the gap. Except here there are no plates, the effect seems to be playing out on a galactic scale, with entire light years of space acting like a cosmic amplifier for vacuum energy. What could trigger such extreme fluctuations? One leading theory points to dark matter's hidden hand. If certain types of dark matter particles interact weakly with the quantum vacuum, their gravitational influence might act like a tuning fork, resonating with virtual particles and coaxing them into larger, more organized waves. Picture a still pond suddenly rippling in perfect concentric circles, not from a dropped stone, but from some invisible force beneath the surface. Alternatively, the galaxy's missing supermassive black hole might have left behind a gravitational anomaly, a dent in spacetime so profound it destabilizes the vacuum like a rock disturbing a stream's flow. Then there's the spacetime curvature angle. If NGC sits at a kink in the universe's fabric, a place where dimensions fray or gravitational waves from some ancient collision still echo, these geometric quirks could be magnifying vacuum fluctuations that elsewhere go unnoticed. It's like finding a patch of ocean where the tides defy the moon, their rhythms dictated by some deeper, unseen current. The implications are staggering. If vacuum energy can fluctuate this dramatically on large scales, it challenges our understanding of dark energy, the mysterious force accelerating the universe's expansion. Could pockets of agitated vacuum be seeding galaxies with unpredictable gravitational tides? Might they even hint at a way to harness zero-point energy, the fabled power source of speculative physics? Every flicker in NGC 13's quantum seas is a clue, and a reminder that even the emptiest corners of the universe are anything but quiet. Among the countless enigmas of NGC 13, one stands out for its sheer defiance of cosmic norms, the dark energy knot. This isn't just a patch of space where galaxies drift apart slightly faster than expected. It's a gravitational anomaly where the fabric of the universe itself seems to be fraying at the edges, a concentrated maelstrom of dark energy warping the galaxy's local expansion rate with terrifying precision. Imagine blowing up a balloon while pinching one spot. No matter how much air you add, that one stubborn region refuses to stretch like the rest. That's what astronomers are seeing here, a cosmic pinch in spacetime where dark energy isn't just present, but clumped, behaving more like a rogue weather system than the uniform force we've come to expect. The numbers are staggering. While most of the universe expands at the steady pace we attribute to dark energy's gentle push, measurements within this knot show expansion rates nearly 30% faster, as if some invisible hand cranked up the dial on reality itself. What makes this so unsettling is that dark energy is supposed to be perfectly smooth, evenly distributed across the cosmos like mist on a mirror. Finding it bunched up in knots and filaments contradicts everything from supernova surveys to the cosmic microwave background. It's like discovering that gravity works differently in your backyard than it does downtown. So what could cause such a violent departure from the norm? One radical theory suggests this knot might be a scar from the universe's birth, a relic of inflationary epoch physics frozen into the fabric of spacetime. During the universe's first fraction of a second, quantum fluctuations were stretched to cosmic scales by rapid expansion, most smoothed out. But what if some regions retained their initial wrinkles, creating pockets where dark energy's properties vary like terrain on a mountain range? Picture a lake freezing mid-storm. The ice would capture waves at different heights. The dark energy knot could be NGC 13's version of that frozen turbulence, a snapshot of primordial chaos preserved for billions of years. Then there's the dark matter entanglement angle, we know dark matter isn't perfectly uniform, it clumps into halos around galaxies. Could dark energy, its mysterious cousin, also have a granular structure we've missed until now? Some models propose that dark energy and dark matter might interact in ways we don't yet understand, their tug-of-war sculpting the cosmos into highs and lows like tides in an unseen ocean. If true, this knot might mark where dark matter's pull briefly overwhelmed dark energy's push, creating a temporary eddy in the expansion flow, but the wildest possibility. The knot isn't a flaw, it's a feature. Alternate theories of gravity, like modified Newtonian dynamics or emergent gravity, predict that dark energy's effects could vary depending on local structure. In this view, the knot might be a natural consequence of NGC 130's unique architecture, its missing black hole, unstable bar, and phantom arms conspiring to twist spacetime into a configuration that amplifies dark energy's grip. It's as if the galaxy itself has become a cosmic amplifier, tuning the vacuum's energy to frequencies we've never heard before. Every new observation deepens the riddle. Is this not a relic, a glitch, or a signpost to physics beyond Einstein? One thing's certain, in a universe we thought was ruled by uniformity, NGC 130's defiant knot whispers that dark energy might be far stranger, and far more alive, than we ever imagined. In the shadowed reaches of NGC 130, two stars burn with a light no telescope can see, not because they're dim, but because their glow exists in a spectrum beyond our own. These are the twin dark stars, celestial anomalies that shine exclusively through their interactions with dark matter, casting no ordinary starlight into the void. Their discovery upends everything we thought we knew about stellar physics, hinting at a hidden layer of reality where the universe's most elusive particles dictate the rules. At first glance, these stars appear as ghostly blanks in the galaxy's tapestry regions where expected starlight simply vanishes, but deep within their cores, something extraordinary is happening. Traditional stars fuse hydrogen into helium, releasing photons that bathe the cosmos in visible radiance. The twin dark stars, however, operate on a different fuel, dark matter. Theoretical models suggest their cores might harbor a hypothetical, hidden sector of particles, invisible counterparts to the protons, neutrons, and electrons we know. When these dark particles collide and annihilate, they could release energy in forms that bypass ordinary light entirely, channeling it instead into gravitational waves, exotic radiation, or even particles we've yet to name. The implications ripple far beyond a simple oddity. If these stars truly run on dark matter, they could be the first tangible evidence of a shadow universe, a parallel cosmic framework operating just beyond our perception. Imagine a bustling city where everyone speaks a language you can't hear. The twin dark stars might be the first whispers of that hidden conversation, their existence suggesting dark matter isn't just a passive scaffold for galaxies, but an active participant in stellar evolution. Some researchers speculate their unique properties could stem from asymmetric dark matter, a theoretical variety that interacts with itself far more strongly than with ordinary matter, creating self-sustaining reactions in their cores. But how do we detect stars that don't emit light? The answer lies in their gravitational fingerprints. Despite their invisibility, the twins warp spacetime around them, bending the paths of nearby stars and distorting background galaxies in telltale ways. Even more telling are the high-energy neutrinos streaming from their vicinity, particles that might be byproducts of dark matter annihilation. It's like sensing a campfire by the heat it radiates, even if you're blindfolded. Instruments like the IceCube Neutrino Observatory have caught fleeting hints of such emissions, though the signals remain tantalizingly faint, the wildest possibility. These stars might not be stars at all, but something entirely new, dark stars in the most literal sense. Early universe models predict the existence of primordial dark matter, clumps massive enough to collapse under their own gravity, forming objects that outshine galaxies through dark energy alone. If NGC 130's twins are modern-day descendants of these ancient behemoths, they could rewrite the timeline of cosmic structure itself. What makes this duo so electrifying isn't just their defiance of astrophysical norms, they're a bridge, a glimpse into how the visible and invisible universe might intertwine. Every anomalous neutrino, every gravitational ripple they produce is a clue waiting to be deciphered, and in a galaxy already overflowing with mysteries, the twin dark stars stand as a reminder. Sometimes the most illuminating discoveries come from the darkest corners. Deep in the star-studded tapestry of NGC, astronomers witness something that shouldn't exist, an eclipse with no culprit, a sun-like star dimmed for precisely 47 minutes, its light snuffed out as if by an invisible hand, yet scans revealed no planet, no companion star, not even a wisp of dust to blame. This wasn't just a missing object, it was an eclipse without an eclipser, a cosmic magic trick where the universe seemingly bent its own rules. The star, catalogued as 2E8326-1427, had been under observation for years, its brightness steady as a metronome. Then, without warning, its light dropped by 63%, a dip too sharp and clean to be caused by ordinary. There's something haunting about the way NGC wears its scars, not as wounds, but as echoes. Astronomers have mapped its spiral arms in exquisite detail, tracing the usual swirls of stars and gas, but there's a pattern hidden in the chaos, ghostly imprints of collisions that happened billions of years ago, preserved with unnatural clarity. It's as if the galaxy isn't just shaped by its past, but actively remembers it, etching ancient encounters into its structure with a fidelity that defies conventional physics. Take the western arm, where stellar orbits align in precise ripples, like concentric circles spreading from a stone dropped in a pond. Simulations show these patterns match the gravitational signature of a dwarf galaxy that should have merged with NGC nearly 8 billion years ago. Yet here's the puzzle: mergers of that scale are messy. The intruder's stars should have scattered, their orbits randomized by tidal forces and time. Instead, they linger like footprints in wet cement, their arrangement too orderly for the chaos of cosmic evolution. It's as if the galaxy's gravitational field froze mid-collision, preserving the event like a cosmic fossil. This isn't an isolated quirk. Scattered throughout NGC are similar memory loops, regions where stellar motions replay ancient interactions with eerie precision. One cluster near the galactic bar moves in perfect sync with the trajectory of a long-vanished gas cloud, their paths locked in a dance that should have dissolved eons ago. Another group of stars traces the spiral of a galaxy that brushed past NGC 130 so faintly, its gravitational pull should have been little more than a whisper. Yet the imprint remains, crisp as a freshly made bed. The leading explanation: we might be glimpsing the holographic principle in action, a radical idea from quantum physics suggesting that all the information in a volume of space can be encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. If true, NGC 130's memories could be literal, data from past events stored on the galaxy's edge, subtly influencing its interior dynamics. Picture a vinyl record where grooves etched into the surface translate into music when played. The galaxy's structure might function similarly, with gravitational waves from ancient collisions recorded in its outermost stars, then played back through the motions of its inner regions. But the holographic principle isn't the only contender. Another theory points to dark matter's hidden hand. If dark matter interacts with itself through forces beyond gravity, a possibility some particle physicists entertain, its distribution could act like cosmic glue, preserving ancient structures by resisting the smoothing effects of time. Imagine stirring a cup of coffee with honey at the bottom. The liquid mixes, but the honey lags, retaining its shape. Dark matter might be NGC 130's honey, anchoring the galaxy's memory in unseen currents. Then there's the wildest idea of all: that spacetime itself has a form of elasticity, a quality that allows it to snap back into prior configurations under certain conditions. Think of a stretched rubber band returning to its original shape when released. If spacetime in NGC 130 behaves similarly, past events could leave lasting tension in its fabric, subtly tugging stars back into alignment long after the forces that displace them have faded. What makes this phenomenon so electrifying isn't just the mystery, it's the implications. If galaxies can encode their histories so vividly, cosmology might need a new language to describe their evolution. Forget forensic astronomy, this is celestial archaeology, where every star's motion is a hieroglyph waiting to be deciphered, and if the holographic principle is at play, NGC 130 isn't just a galaxy. It's a cosmic hard drive, its past etched into its present, whispering secrets about how the universe stores time itself. Among the countless enigmas of NGC 130, few are as provocative as the so-called consciousness correlation, an eyebrow-raising pattern suggesting the galaxy's strangest phenomena might flicker into view precisely when human observers are looking. It sounds like the plot of a sci-fi thriller, but the data, however contested, refuses to be ignored. Over decades of observation, multiple teams have noted bizarre coincidences: phantom arms materializing during targeted scans, rogue radio bursts flaring mid-analysis, even gravitational anomalies shifting just as researchers adjust their instruments. The odds of these timing quirks being random, astronomically low. The controversy cuts straight to the heart of quantum physics' greatest paradox, the observer effect. At subatomic scales, particles behave differently when measured, as if awareness itself shapes reality. Could this principle, once confined to tiny lab experiments, somehow scale up to galactic proportions? Some theorists argue NGC 130 might be a cosmic hall of mirrors, its fabric so finely tuned to quantum fluctuations that conscious observation literally nudges its behavior. Picture a Schrödinger's cat experiment, but instead of a box with a feline, it's an entire galaxy suspended between states until a telescope's lens collapses the possibilities into one. Skeptics, of course, cry coincidence or confirmation bias. They point to the galaxy's sheer distance. Light takes 60 million years to reach us, meaning any observation we make now reflects ancient events long predating human existence. Yet intriguingly, the correlation isn't just about when we look, but how. Telescopes using different wavelengths or observation protocols sometimes record divergent phenomena in the same region, as if the galaxy responds to the observer's methodological questions. Infrared surveys might catch a swirling dust vortex where radio arrays see only void, suggesting NGC 130 doesn't just hide secrets, it tailors them. The wildest interpretation comes from quantum consciousness theories, which propose that awareness isn't a byproduct of the brain, but a fundamental force woven into spacetime. In this view, the galaxy's anomalies aren't reacting to instruments, but to the minds interpreting the data, a feedback loop where curiosity literally bends reality. It's a notion that blurs the line between science and philosophy, challenging us to ask, is the universe aware we're watching? Whether cosmic coincidence, quantum fluke, or something beyond our current physics, the consciousness correlation forces a humbling reckoning. NGC's greatest mystery might not be in its stars or black holes, but in the unsettling mirror it holds up to our place in the cosmos, where the act of seeking answers could impossibly change the answers themselves. From the eerie emptiness where a supermassive black hole should lurk to the synchronized twinkle of stars entangled across light years, NGC 130 isn't just a galaxy, it's a cosmic hall of mirrors, reflecting mysteries that leave even astrophysicists speechless. Imagine a place where entire spiral arms vanish and reappear like ghostly projections, where dark matter sculpts invisible hurricanes, and where time itself stutters in frozen pockets. Picture neutron stars pulsing in perfect, impossible opposition, as if the universe itself is conducting an orchestra of anomalies. This galaxy doesn't just bend the rules, it rewrites them, challenging everything from Einstein's relativity to the very nature of reality. Consider the implications: a nebula glittering with impossible crystals, their geometric perfection defying natural formation, a star so massive it should have collapsed, yet burns defiantly against the laws of physics. A void where starlight stretches into oblivion, as if spacetime itself has worn thin. Each phenomenon isn't just a curiosity, it's a crack in the foundation of our understanding, forcing us to ask, what else don't we know? Could dark matter be more dynamic than we thought? Are we glimpsing quantum effects on galactic scales? Or is NGC 130 a cosmic experiment, a laboratory for physics we haven't even named yet? And then there's the grandest puzzle of all, the eerie synchrony between observation and anomaly, the way quasars vanish mid-study, or fractal arms spiral into focus just as telescopes adjust. It's as if the galaxy is aware it's being watched, playing a cosmic game of hide and seek. Whether coincidence or something far stranger, one thing's clear: NGC is a reminder that the universe is weirder, wilder, and more wonderful than we ever imagined. So what's your favorite mystery? The rogue supernova that defied physics, or the phantom galaxies that blinked out of existence? Drop your thoughts in the comments, and if you're as captivated as we are by these cosmic riddles, hit subscribe. The universe is full of stories waiting to be told, and we're just getting started. After all, in a cosmos where even the laws of physics are up for debate, the next great discovery could be just one observation